Hello there, and welcome to the Cosmographer. The radio sky of our universe is 6 times louder than every known source combined, every galaxy, every quasar, every pulsar, and after nearly 20 years, nobody can say why. That is the first unsolved mystery in tonight's catalogue, and it is far from the strangest. Before this night is over, you will hear how the heart of our galaxy destroys kilograms of antimatter every second, fed by a factory no one has found. How starlight everywhere carries more than 550 fingerprints that a full century of chemistry has failed to read. How spacecraft leaving Earth have changed speed by millimeters per second against every equation we trust, and were never explained. And how a count of 1.36 million quasars now suggests the universe itself may be moving in a way our best theory cannot allow. 24 real, measured, still open mysteries, arranged across 7 parts and more than 4 hours. Get comfortable and settle in. If falling asleep to the universe's unsolved case files sounds like your kind of night, a quick like and subscribe helps this channel reach more curious minds like you. Because by the end of this catalogue, you will know why the last mystery on the list is not out there at all. It is about you. Now, let's begin with a sound that has no source. Part 1. The signals nobody can trace. Everything you are about to hear is real. Every signal in this catalogue was recorded by an actual instrument, checked by actual people, and published for the world to examine. And every single one of them remains, as of tonight, unexplained. That is the organizing rule of the next 4 hours. This is not a collection of legends, or rumors, or stories that grow taller with each telling. This is a walk through the universe's open case files, the measurements that refuse to fit, the objects that should not exist, the numbers that will not add up, each one presented with what we know, what we suspect, and an honest label on what remains unsolved. There are 24 mysteries on this list, arranged into 7 parts. We will begin with signals, light and vibration arriving from the sky with no accepted source. We will move through starlight we cannot translate, explosions that break their own categories, and the decorated, misbehaving heart of our own galaxy. We will meet galaxies that should not exist, and then come all the way home, to spacecraft in our own neighborhood that change speed without permission, and to the strange painted wall of our own solar system. And at the end, we will arrive at the largest open questions there are, the places where the universe's own arithmetic refuses to balance. A word on what you will not find here. You will not find the famous staples that fill every list of this kind. The mysteries tonight are the ones that rarely make those lists, and several of them will likely be new to you even if you have spent years with this subject. Some have been open for a century. Some opened within the last 3 years. A few are being fought over by working scientists this very season, and where a mystery is actively being cornered, I will say so plainly. One more thing before we begin. It is easy to assume that an unsolved mystery is a failure, that somewhere, someone dropped the thread. The truth is closer to the opposite. Each of these cases stays open because thousands of careful people keep testing every easy answer and finding it wanting. An open case, in science, is a kind of promise. It means the universe still has something to say that we have not heard yet. A brief word, too, on how to listen tonight. Each case will be told the same way. First, what was actually measured, the instrument, the date, the people, then what the measurement should have shown, then what it showed instead, and finally, the honest state of the argument. Where a mystery is contested, you will hear both sides. Where a claim has been partly explained, I will say so rather than let it wear a costume of mystery it no longer deserves. Numbers will arrive with company, every figure paired with something you can hold in your mind, because a number you cannot feel is just noise with digits. You do not need to retain any of it. The catalogue is built so that each case stands alone, drift off during one mystery, and the next will greet you without complaint. There is no quiz at the end of the universe. So dim the lights, settle into whatever position carries you through the night, and let the catalogue begin. We start with the simplest kind of mystery there is, a sound with no source. In July of 2006, in the pre-dawn dark of Palestine, Texas, a team from NASA's Goddard Space Flight Center prepared to launch a balloon. Their experiment was called Arcade-2, the absolute radiometer for cosmology, astrophysics, and diffuse emission, and it was led by a physicist named Alan Kogut. The plan was almost humble. The balloon would carry a set of radio antennas to the edge of the atmosphere, far above the interference of cities and weather, and take the temperature of the radio sky. Kogut's team hoped to find the faint, accumulated warmth of the universe's very first generation of stars, a whisper from the beginning, buried beneath everything else. Picture the launch. The balloon fills slowly in the darkness, a film of plastic thinner than a sandwich bag, pale under the floodlights. It rises, and as the air thins around it, it swells until it could swallow a football stadium. At 120,000 feet, 3 times the cruising altitude of any airliner, the sky above it is violet black, the curve of the Earth shows at the horizon, and the instruments open their eyes. The antennas themselves are bathed in liquid helium, chilled to about 2.7 degrees above absolute zero. That number was chosen with care. It is the temperature of the cosmic microwave background, the afterglow of the Big Bang itself, which means the instrument is exactly as cold as the oldest light in the universe. An antenna that cold adds almost nothing of its own. Whatever it hears honestly. What it heard has never been explained. Instead of a whisper, Arcade-2 recorded a roar. The radio sky, at the frequencies Kogut's team measured, was roughly 6 times brighter than it had any right to be. Add up every known source of radio emission in the universe, every galaxy, every quasar, every pulsar, every cloud of glowing gas ever catalogued, and the sky Arcade-2 measured is about 6 times louder than that total. The team assumed at first that something was wrong with the instrument. That is the correct first assumption, and they took it seriously. They spent close to 3 years hunting for the error, a leak of warmth, a miscalibration, a reflection from the balloon itself. They found nothing. In January of 2009, they announced the result, and the signal acquired its informal name, the space roar. Here is what makes the roar so stubborn. It was not, in the end, a single balloon's claim. When astronomers went back through decades of ground-based radio surveys, measurements stretching from 22 megahertz up to 10 gigahertz, taken by different instruments in different countries across different decades, the same excess was quietly sitting in the data. The sky really is too loud, across a wide sweep of the radio dial, and it has been too loud the whole time. The signal even has a formal name now, the radio synchrotron background. Synchrotron radiation is the light given off by electrons spiraling along magnetic field lines at close to the speed of light. It is one of the most ordinary processes in astronomy. The mystery is not what kind of light this is. The mystery is that there is 6 times too much of it. Every explanation offered so far has run into a wall. Suppose the roar comes from countless faint radio galaxies, too dim to catalogue individually. The problem is that galaxies which emit radio waves also emit infrared light, in a tight, well-measured relationship that holds across the entire sky. Enough hidden galaxies to produce the roar would produce a matching infrared glow, and that glow is not there. Suppose instead the roar comes from hot gas, drifting between galaxies in great clusters. Measured cluster gas falls short by a wide margin. Suppose our own galaxy is wrapped in an unseen halo of radio emission. Then other spiral galaxies should wear the same halo, and when we look at spirals edge-on, they do not. The exotic proposals remain: annihilating dark matter, the first black holes, a generation of enormous primordial stars, but each is a guess without a confirmation. In 2022, the community held an entire workshop devoted to the problem, and their published summary used careful, deliberate language. This is the least understood electromagnetic background in astronomy. It is worth appreciating how much care went into the measurement itself, because the space raw's credibility rests on it. The heart of Arcade 2 was a device almost comically dedicated to honesty, a large external calibrator, a target of known temperature that the instrument could swing in front of its antennas mid-flight, comparing the sky against a reference again and again, thousands of times, at altitude. Most radio telescopes measure differences across the sky and cannot tell you the sky's absolute brightness at all. Arcade 2 was engineered to answer exactly that harder question, the way a good scale is engineered around a reference weight. When the team says the radio sky is 6 times too bright, they are not comparing one patch of sky to another. They are comparing the whole sky to a laboratory standard hanging in the stratosphere. The RAW also casts a long shadow forward through this catalogue, and it is worth flagging now. Cosmologists want, badly, to use low-frequency radio light to explore the universe's dark ages, the era before the first stars, when hydrogen alone filled space. Every such measurement must be made against the backdrop of the radio sky, which means every such measurement inherits the RAW as an uninvited guest. An unexplained background, 6 times brighter than expected, is not merely a curiosity. It is a fog bank, parked in front of one of the last unexplored eras of cosmic history. Some researchers have even wondered aloud whether the RAW might be a signal from that era, the radio glow of some process in the young universe that no theory currently contains. If so, the fog bank is the discovery. Keep that thought. It will return, quietly, when we reach a small antenna in the Australian desert later tonight. And there is one more possibility that the community keeps on the table with commendable discipline, that some subtle, shared error afflicts the measurements, a mismodeling of our own galaxy's radio glow, which must be subtracted before the extragalactic background can be seen. The galaxy is subtracted using models of its shape, and models can be wrong. But here the RAW's defenders point to a stubborn fact. Analyses using different galaxy models, different instruments, and different frequencies keep converging on an excess of similar size. To make the RAW vanish, the Milky Way would need to be hiding a radio halo of a kind that, as far as we can measure, no other spiral galaxy possesses. The cure, in other words, requires a mystery at least as large as the disease. Sit with how strange that is for a moment. This is not a flicker at the edge of detection. In the radio sky, this signal is not a detail. It is most of what there is. If your eyes saw in radio light, the space between the stars would glow, everywhere, with a light whose author has never been identified. When you tune an old radio between stations, a small part of that static is the Big Bang's afterglow. That part we understand. But a larger share of the sky's static comes from somewhere else, and after nearly 2 decades of checking, nobody can say where. The RAW earns its place at the start of this catalogue because of what it did to the people who found it. An instrument built to hear one thing heard another. That is worth remembering, because it will happen again before this night is over, with a space telescope and with a small spacecraft parked at the edge of the sun's influence. The universe has a habit of answering the question nobody asked. And radio static is not the only thing pouring out of the sky in impossible quantities. The next signal on this list is stranger than static. It is the light of antimatter dying, by the ton, at the heart of our own galaxy. Antimatter sounds like an invention of fiction, but it is as real as the chair beneath you. Every particle of ordinary matter has a mirror twin, same mass, opposite electric charge. The electron's twin is called the positron. And the defining fact about antimatter is what happens when it meets its counterpart. The two annihilate, converting their entire mass into light. Not a burn, not an explosion in the chemical sense, a complete conversion, the most efficient release of energy that physics allows. When an electron and a positron destroy each other, they emit gamma rays at one precise, unmistakable energy, 511 kilo-electron volts. That number is a signature. Nothing else in nature produces a sharp line of light at exactly that energy. If you detect it, you are watching antimatter die. In the early 1970s, balloon-borne gamma-ray detectors lifted above the atmosphere began to see exactly that line, shining from the direction of the center of our galaxy. The first hints came in 1972 from a Rice University team, and by the end of that decade, the energy had been pinned precisely, 511 kilo-electron volts, the annihilation signature, glowing steadily from the heart of the Milky Way. Somewhere in there, positrons were dying in enormous numbers, which meant something was making them in enormous numbers. The instrument that turned this from a curiosity into a standing mystery was a European satellite called Integral, launched in 2002, carrying a spectrometer built to map the gamma-ray sky. For more than 20 years, Integral has charted that annihilation line, and its map is the heart of the problem. The glow is not spread along the galaxy's disk, where the young stars live and die. It is concentrated in the bulge, the old, quiet, rounded swarm of ancient stars at the galaxy's center. Measured against the disk, the bulge dominates in a way no known population of objects can explain. And the implied numbers are difficult to hold in your head. To sustain that glow, roughly 10 to the 43rd power positrons must be annihilating every single second, a 1 followed by 43 zeros. Every second. Sustained for at least the 50 years we have been watching, and presumably for far longer. Let me give that number a body. Antimatter is the most expensive substance human beings have ever produced. Particle accelerators can make it, one particle at a time, at fantastic cost. By most estimates, manufacturing a single gram would consume trillions of dollars and centuries of accelerator time. All the antimatter humanity has ever created, gathered together, would not weigh as much as a grain of sand. Meanwhile, the center of our galaxy destroys kilograms of the stuff every second, as a matter of routine, and has done so since before our species existed. Whatever runs that factory has never been identified. The candidate list is long, and every candidate has a problem. Dying massive stars forge radioactive elements, aluminum-26, titanium-44, whose decay releases positrons, and this accounting works reasonably well for the disk of the galaxy. But it fails for the bulge, because the bulge's stars are old, and its supernovae are too few. X-ray binaries, star systems where a black hole or neutron star tears gas from a companion, can spray positrons into space, and pulsars can too. Plausible contributors, wrong map. They do not cluster the way the glow clusters. Sagittarius A star, the supermassive black hole at the galaxy's exact center, might have produced floods of positrons during past outbursts. Possible and unproven. And then there is the elegant, unnerving option that the bulge's glow traces dark matter itself, light dark matter particles annihilating into electron-positron pairs, which then annihilate in turn. The shape fits. The evidence, beyond the shape, does not yet exist. The line itself carries more forensic information than you might expect, and it deepens the puzzle. A positron does not usually annihilate the instant it is born. it must first slow down, shedding energy in the interstellar gas, and most positrons end their existence gently, briefly forming an exotic pseudo-atom called positronium, an electron and positron orbiting one another for a fraction of a second before mutual destruction. The spectrum measured by integral shows that the vast majority of the galaxy's positrons, over 90%, die this way, in cool, partly ionized gas, not in violent environments. That is a clue with teeth. Whatever creates the positrons, they are annihilating in the galaxy's quiet neighborhoods, after long journeys or gentle births. It rules out the most dramatic scenarios and disciplines all the others. The distances involved discipline the theories further. A positron born in the disk cannot easily commute to the bulge. Charged particles ride magnetic field lines, and plausible transport calculations struggle to move enough of them inward before they annihilate en route. So either the source lives in the bulge itself, among the old stars where positron factories are scarce, or something ferries antimatter across thousands of light-years more efficiently than we understand. Each escape from the map problem creates a transport problem, and each escape from the transport problem creates a map problem. The mystery is a closed loop, which is precisely why it has survived 50 years. There is also a historical texture here worth savoring. This line was the first gamma-ray spectral line ever detected from beyond the solar system. Antimatter announced itself before most of the gamma-ray sky had been mapped at all. The pioneers flew their detectors on balloons from Texas and Australia, instruments swinging beneath polyethylene film at the edge of the atmosphere, and the line they found has now outlived several generations of the satellites sent to study it. When COSY takes up the case, it will be the fourth great instrument era to inherit the same unanswered question, half a century of steadily better eyes, all watching the same quiet, industrial destruction of antimatter at the center of the galaxy, all returning the same verdict of source unknown. Try for a moment to picture the thing itself, because the mind's eye is the only instrument that renders gamma rays. Face the constellation Sagittarius on a southern summer night, toward the teapot of stars that marks the galaxy's heart, and imagine your vision sliding up the spectrum, past visible light, past X-rays, into the hard glare where annihilation lives. The crowded starfields would fade like fog burning off, and in their place, wrapped around the galactic center, would hang a soft, structureless luminescence, the width of dozens of full moons, the annihilation fog, shining at one pure color no natural flame can produce, brightest at the core and thinning outward through the ancient stars of the bulge. It would not flicker. It has not measurably changed in the 50 years instruments have watched it. Steady, sourceless and antique, it would be the sky's most serene feature, and every photon of it would mark the grave of a particle of antimatter that existed, briefly, somewhere in the heart of the galaxy, for reasons no one alive can state. There is also a sharp scientific consolation embedded in this mystery, worth naming before we leave it. Whatever the bulge's positron factory is, its output sets one of the cleanest constraints in all of astroparticle physics. Any theory of dark matter, any model of black hole activity, any proposed population of hidden compact objects in the inner galaxy must pass a simple audit, produce enough positrons to feed the glow, or at least not produce too many. Dozens of otherwise attractive theories have quietly died against that ledger. This is the underappreciated dignity of unsolved signals, even unexplained. They discipline everything else. The fog has spent 50 years refusing to name its maker, and in that same 50 years it has been silently vetoing wrong ideas about the galaxy's heart, a judge who will not speak but rules constantly. 2 decades of mapping have added texture without adding an answer. The most recent analysis of Integral's full 20-year record, published in 2025, found the bulge's glow is not even symmetric. It leans, subtly, in a way nobody predicted, and found hints of annihilation light associated with a nearby region of massive young stars, which would support the radioactive decay story for at least part of the signal. Every such detail narrows the field slightly. None of it names the factory. A NASA mission called COSI, the Compton Spectrometer and Imager, is being prepared for launch around 2027, designed specifically to photograph this line with sharper eyes than integrals. It may finally resolve the glow into sources. Or it may do what better instruments so often do in this catalogue, and hand us a stranger map than the one we had. For now, the plain summary is this. In the direction of Sagittarius, about 26,000 light-years from where you are lying, the oldest neighborhood of our galaxy is wrapped in a fog of dying antimatter, fed by a source with no name. It has been glowing there through every night of human history. You have simply never had eyes that could see it. And the positron fog is not the only anonymous glow hanging over the galaxy's heart. There is another, higher in energy, subtler in shape, and it may be the most consequential smudge of light in modern physics. In June of 2008, NASA launched the Fermi Gamma-ray Space Telescope, an observatory that sweeps the entire sky every 3 hours, cataloguing the universe's most violent light. Within a couple of years, astronomers sifting Fermi's data, Lisa Goodenough and Dan Hooper were among the first, tried a simple exercise. Take the inner galaxy. Subtract everything we know, the pulsars, the supernova remnants, the glow of cosmic rays striking gas clouds, every catalogued source, every mapped process. In a well-behaved galaxy, what remains after that subtraction should be approximately nothing. What remained instead was a glow. Smooth, round, centered on the galactic center, extending thousands of light-years outward, with its brightness peaking at energies of a few billion electron volts. It has become known as the Galactic Center GeV excess, and it has now survived 15 years of attempts to erase it. The reason this faint smudge commands such attention is the first of its two possible explanations. The excess happens to match, in its energy spectrum, in its round shape, in its smooth fall-off with distance, almost exactly what theorists predicted dark matter would produce. Dark matter, the invisible substance whose gravity holds galaxies together, outweighs ordinary matter 5-to-1 in the universe at large, and it should pool most densely at the galaxy's center. If dark matter particles are their own antiparticles, as many leading theories propose, then where they crowd together, they should occasionally collide and annihilate, releasing gamma rays. Particles with masses of roughly 30 to 70 billion electron volts would produce a glow peaking at a few billion electron volts, spherical, smooth, centered on the galactic center. That is a description of the excess. For a substance that has never once revealed itself except through gravity, this smudge could be the first direct light dark matter has ever shown us. But there is a second explanation, and it is entirely mundane. Millisecond pulsars are ancient neutron stars, the collapsed cores of dead suns, spun up by feeding on companion stars until they rotate hundreds of times per second. Each one emits gamma rays, faintly, steadily, in roughly the right spectrum. No single one at the galactic center would be individually detectable. But the old, dense bulge of the galaxy could plausibly host thousands of them, unseen, their combined light blending into a smooth haze. A swarm of dead stars, masquerading as new physics. It is worth pausing on how difficult the subtraction at the heart of this mystery actually is, because the entire anomaly lives downstream of it. The inner galaxy is the most complicated place in the gamma-ray sky. Cosmic rays, protons accelerated by supernova shocks, slam into interstellar gas clouds and spray gamma rays. Electrons scatter starlight up to gamma-ray energies. Hundreds of catalogued point sources crowd the field. Modeling all of that means modeling the galaxy's gas maps, its radiation fields, its magnetic structure, and its cosmic ray sea, each imperfectly known. The excess is what remains when the model is subtracted from the data, which means the excess is, unavoidably, hostage to the model. Skeptics have argued for years that some of the signal could be an artifact of imperfect foregrounds. Yet the excess has now survived a dozen generations of improved models, alternative gas maps, and independent analysis pipelines. Whatever it is robust. The argument is only ever about its interpretation, not its existence. Two further clues cut in opposite directions, which is the signature of a genuinely balanced mystery. The excess's detailed shape appears, in several analyses, to trace the galaxy's boxy stellar bulge, the actual distribution of old stars, rather than the smooth sphere dark matter should form. Stars trace stars. That finding leans toward pulsars. But dark matter's defenders note a second ledger. If dark matter particles of the required mass were annihilating at the galactic center, they should also annihilate, faintly, in the dwarf galaxies orbiting the Milky Way, clean, dark matter-dominated systems with no pulsar contamination. Searches there have found suggestive whispers in some dwarfs and silence in others, hovering at the edge of sensitivity. Not a confirmation, not quite an exclusion. The universe has arranged, with what feels like deliberate mischief, for every cross-check to return an answer just short of decisive. And hovering over the entire question is its price tag. The particle the optimistic reading requires, a weakly interacting massive particle in the tens of billions of electron volts, is precisely the particle that underground detectors on Earth have spent 30 years failing to catch, in ever quieter laboratories beneath ever deeper rock. If the galactic center excess is dark matter announcing itself, it would mean the particle physicist's most wanted fugitive has been visible this whole time, not in a mine in South Dakota, but hanging as a faint light over the center of the galaxy, waiting for the pulsar hypothesis to be eliminated so it could claim the case. The two explanations have fought to a draw for 15 years, and the seesaw has been remarkable to watch. In the mid-2010s, statistical analyses of the excess reported graininess, a subtle clumpiness in the light, suggesting point sources rather than a smooth particle glow. Pulsars surged ahead. Then those methods were themselves dissected, and flaws were found in how they handled the galaxy's messy foregrounds. The seesaw leveled. In the most recent rounds, machine learning analyses have found the excess's shape and statistics consistent with a millisecond pulsar population, while radio astronomers point out that the required thousands of pulsars have stubbornly failed to turn up in searches, and the dark matter interpretation has never been ruled out. Both explanations remain complete. Both remain unproven. That almost never happens in science for this long, and it tells you how carefully each side has done its work. What breaks the tie will likely be new instruments. Radio arrays like Meerkat in South Africa and the planned next-generation Very Large Array can hunt the bulge for the individual pulsars the mundane story requires. If they find hundreds, the case closes quietly, and a swarm of dead stars takes the credit. If exhaustive searches keep coming up empty, the dark matter reading strengthens toward the extraordinary. There is even a proposal to settle it with gravitational waves, since a hidden pulsar population would leave its own subtle imprint for future detectors. Consider what is actually at stake in that faint leftover light. Dark matter passes through you constantly, through your body, your home, the Earth itself, without leaving a mark. It has shaped every galaxy that exists while declining every invitation to introduce itself. If the GGXS is what the optimists think it might be, then the introduction has already happened. It is sitting in Fermi's data, a smudge 5,000 light-years wide, waiting for us to become certain. And if it is pulsars after all, we will have discovered a hidden graveyard of thousands of dead stars at the heart of our galaxy, which is, by any fair measure, also a remarkable thing to find behind a smudge. From light we cannot source, we turn now to something stranger still, a vibration in the fabric of space itself, detected not with any telescope, but with a network of clocks made from dead stars. A millisecond pulsar is one of the strangest gifts nature has ever handed astronomy. It is the collapsed core of a dead star, a sphere heavier than the sun, compressed to the size of a city, spinning hundreds of times every second, sweeping a beam of radio waves across space like a lighthouse gone feral. The gift is the regularity. The pulses from these objects arrive with a precision that rivals the best atomic clocks humans have ever built. Time one for years, and you can predict its next pulse to within a few tens of nanoseconds, a few hundred millionths of a second. Nature scattered perfect clocks across the galaxy, free of charge, and about 25 years ago a group of astronomers realized what a network of perfect clocks could be used for. The collaboration is called NanoGrav, the North American Nanohertz Observatory for Gravitational Waves, and its idea is elegant. Gravitational waves are ripples in space itself, stretching and squeezing distance as they pass. The waves that LIGO detects from colliding black holes oscillate hundreds of times per second. But theory predicted a slower music, waves with periods of years to decades and wavelengths measured in light years rolling through the galaxy continuously. No instrument on Earth could ever be large enough to feel them. A network of pulsar clocks, spread across thousands of light years, could. As a wave passes between a pulsar and the Earth, the space the pulses cross is alternately stretched and compressed, and the ticks arrive early, then late, by billionths of a second, in a slow rhythm. One pulsar drifting off schedule means nothing. But dozens of pulsars, drifting in a correlated pattern that depends on their angular separation in the sky, a mathematical signature worked out decades ago and known as the Hellings-Downs curve, could mean only one thing. On June 28, 2023, NanoGrav announced the result of 15 years of patience, 68 pulsars, timed for a decade and a half, showing exactly that correlated pattern. The same day, parallel collaborations in Europe, Australia, India, and China released consistent findings. The conclusion, stated plainly, is one of the most remarkable sentences in modern science. The universe is humming. A background of gravitational waves, with wavelengths of light years, is passing through the galaxy, through the solar system, through the room you are lying in, at all times, from all directions. As you listen to this, the distance between the Earth and every star in the sky is swelling and shrinking, rhythmically, by roughly the width of a football field per light year of separation. You have been riding that swell your entire life. The presumed composer is a population of the largest objects in existence. When galaxies merge, and galaxy mergers are how the universe builds its largest structures, the supermassive black holes at their centers, millions to billions of times the sun's mass, sink together and form a binary, orbiting each other for millions of years. Each such pair broadcasts gravitational waves in exactly the band the pulsar networks hear. The hum, in this reading, is the combined voice of every supermassive black hole pair in the observable universe, hundreds of thousands of them, all singing over one another, a chorus with no beginning and no end. There is something almost companionable in that thought. The loudest sound in the universe, if we may call it a sound, is a low chord made of endings, every pair of merging galaxies that ever committed to one another, held in a single sustained note. But this detection carries two genuine mysteries, and they are why the hum belongs in this catalogue. The first is its volume. When theorists model the universe's population of merging galaxies, how many, how massive, how often, The hum they predict comes out quieter than the hum we hear. Not wildly quieter, but persistently so, by a factor that resists easy adjustment. Either the universe makes more giant black hole pairs than we believe, or grows them heavier than we believe, or something else is contributing to the chord. And the candidate list for that something else is not modest. Cosmic strings left over from the universe's birth, primordial black holes, exotic phase transitions in the first second of time. The hum is real. Its loudness is unexplained. Consider for a moment what it takes to make this measurement at all, because the method is among the most patient in science. Each millisecond pulsar must be observed for years, some for decades, with its every pulse arrival time logged to nanosecond precision. From those logs, astronomers must strip away everything that is not gravitational waves: the pulsar's spin down, its motion through space, the dispersion of its pulses by interstellar plasma, which itself changes as the galaxy drifts, the wobble of every planet in our solar system tugging the Earth-based telescopes around the Sun. The solar system's own center of mass must be known to meters. An error in Jupiter's calculated position shows up in the data. When nanograv announces a correlated pattern across 68 pulsars, it is announcing victory over every one of those contaminants simultaneously, sustained for 15 years. There are few achievements in observational science with that ratio of patience to signal. The hum's discovery also opens a hunt that will define the coming decade, finding individual voices in the chorus. The background is the summed song of countless binaries, but the loudest few, the closest, heaviest pairs, should eventually stand out as individual tones, continuous waves at a single frequency coming from a single patch of sky. Candidate host systems already exist. Certain galaxies show nuclei that wobble or flare with suspicious regularity, and one famous quasar has flared on a years-long cycle for over a century, interpreted by some as a binary's orbital clock. When the first individual pair is confirmed in the timing data, an event plausibly within this decade, astronomers will be able to point at one specific galaxy and say, there, at those coordinates, two black holes with a combined mass of billions of suns are in their final spiral, and we can hear them. The universe's largest objects will acquire addresses. And a further prize hides in the hum's texture. If the chord comes from discrete binaries, it should not be perfectly smooth across the sky. It should be slightly lumpy, louder toward the sky's richest concentrations of massive galaxies. Mapping that lumpiness would turn the hum into a census of the universe's most massive black hole pairs, weighed collectively by space-time itself. If instead the hum proves eerily uniform, the exotic alternatives, cosmic strings, primordial ripples from the first second, climb back up the suspect list. Either way, the nanohertz sky has become what the gamma-ray sky was in 1970, and the gravitational wave sky was in 2015. A brand new spectrum, just opened, with its first great mystery already inside. The second mystery is older and sharper, and it goes by a wonderfully specific name, the final Parsec problem. Follow two supermassive black holes after their galaxies merge. Friction with stars and gas drags them inward efficiently, from tens of thousands of light-years apart, down to a few light-years. And there, according to decades of theoretical work, the machinery stalls. By that point, the pair has gravitationally flung away every star that ventured close, emptying their surroundings. Gravitational waves alone cannot yet carry away their orbital energy at that separation. On paper, the two giants should hang there, a parsec apart, circling for longer than the age of the universe, close enough to feel each other, forever forbidden to touch. If that were the whole story, the nanohertz sky would be nearly silent. The hum says otherwise. The hum says the universe crosses the final parsec routinely, resolving in practice a problem we have not resolved on paper. Perhaps gas disks grease the passage. Perhaps lopsided galaxies keep funneling fresh stars into the gap. Perhaps a third black hole arrives with the next merger and shoves the pair together. Something works. We do not know what. Keep that phrase with you as the night goes on. Nothing in the universe stands still. Even the emptiest stretch of space between you and the nearest star is trembling, at this moment, with the slow chord of the universe's heaviest objects. We will meet that idea once more, near the very end of this list, wearing a different and stranger face. For now, we leave the signals behind. The second part of this catalogue concerns light itself, light that arrives intact, legible, and untranslated. And it begins with the oldest unsolved case in all of astronomy. Part 2. The Light We Cannot Read. In 1919, at the Lick Observatory on Mount Hamilton in California, a graduate student named Mary Leah Hoag was doing exacting, unglamorous work, photographing the spectra of binary stars, night after night, on glass plates. A spectrum is starlight, fanned out into its component colors, and crossing it are dark absorption lines, the fingerprints of atoms and molecules that have drunk specific colors out of the light. Hoag's binary stars were spectroscopic pairs, two suns orbiting one another, and their motion is written in those lines. As each star swings toward the Earth and away, its lines shift blueward and redward, in rhythm with the orbit, a slow metronome of Doppler shifts. Every line in such a spectrum dances. That is the entire point of observing them. Put yourself in that dome for a moment. It is a working night in 1919 on Mount Hamilton, the observatory reached by a stagecoach road with 365 turns, one for each day of the patience the work requires. The dome is unheated because warm air shimmers and ruins the images. The astronomer's coat is buttoned to the collar. Mary Leah Hoag guides the great refractor by hand and eye, holding a star steady on the spectrograph's slit for an exposure that consumes hours, the only sounds the clock drives soft ticking and the wind against the shutter. The starlight she is collecting has traveled for centuries. Tonight it ends its journey by biting its signature into a glass photographic plate, angstrom by angstrom. Later, in daylight, she will bend over the plate with a measuring engine and log each line's position to 1,000th of a millimeter, entry after entry, the profoundly ordinary bookkeeping from which astronomy is actually made. It is in exactly this kind of hour, cold, patient, procedural, that the century's quietest mystery first surfaces, 2 entries in the ledger that decline to move. 2 lines were not dancing. At wavelengths of 5,780 and 5,797 angstroms, in the yellow part of the spectrum, Hoag recorded 2 absorption features that sat perfectly still while every stellar line swung around them. The stillness had a clear meaning. Whatever was absorbing those 2 colors was not part of either star. It was somewhere in between. In the enormous stretches of nominally empty space, the starlight crossed on its way to California. Something out there, in the dark between the stars, was drinking 2 precise colors out of every beam of light that passed. In the 1930s, the astronomer Paul Merrill took up those stationary lines, confirmed they were interstellar, and began finding more. The features earned a name, the diffuse interstellar bands. Diffuse, because unlike the crisp, needle-sharp lines of atoms, these bands are oddly broad and soft-edged, blurry fingerprints. And over the following century, the catalogue grew and kept growing. Modern surveys using instruments Hoag could not have dreamed of have now mapped more than 550 distinct bands, spread from the near ultraviolet across the visible and into the infrared. They appear along essentially every line of sight through the galaxy's dust and gas. They strengthen where interstellar material thickens. They correlate with each other in families, hinting at shared origins. They are, without question, the fingerprints of substances that fill interstellar space throughout the Milky Way, and, as other galaxies confirm, beyond it. Here is the standing of the case after 107 years. The carriers of more than 99% of those 550 bands are unknown. Unknown, not disputed, not narrowed to 2 candidates. Unknown. This is very likely the longest-running unsolved mystery in the history of astronomy, and it is almost startling how few people outside the field have ever heard of it. We hold in our archives the fingerprints of hundreds of distinct substances that permeate the galaxy, taken with exquisite precision, reproduced across thousands of sightlines. And after a century of laboratory chemistry, a century of synthesizing candidate molecules, freezing them to interstellar temperatures, and comparing their absorption against the sky, we have secured an identification for one. One carrier in 107 years. That single victory is worth telling properly, because it shows the scale of the labor involved. The molecule is Buckminster fullerene, 60 carbon atoms arranged in a closed cage, the shape of a soccer ball, in its electrically charged form. Laboratory chemists led by John Mayer in Basel, Switzerland, spent more than 2 decades developing the technique to measure that ion's absorption spectrum at the temperature and isolation of deep space, a feat of experimental patience that consumed careers. In 2015, the measurement finally succeeded, and it matched a small set of bands in the near-infrared. 4 or 5 bands out of more than 550. The community celebrated, properly, for the first confirmed carrier in a century of trying. Then everyone looked back up at the remaining 540-some fingerprints, still unclaimed. The scale of the search space explains a century of failure better than any excuse could. The band's properties point to large molecules, perhaps 20 to 100 atoms, probably rich in carbon. Count the chemically plausible structures in that size range, and the number runs into the millions. Each candidate must be synthesized or isolated, cooled to interstellar temperatures, a few degrees above absolute zero, held in a vacuum better than interplanetary space, and measured in its electrically charged states as well as its neutral one, because interstellar radiation strips electrons from molecules routinely. A single candidate can consume a laboratory for years, as Buckminster fullerene did. The universe, meanwhile, holds its 550 answers fixed in the light, unchanged from decade to decade, with the patience of something that has never needed a deadline. The strongest current suspects deserve naming. Polycyclic aromatic hydrocarbons, flat, chicken wire lattices of fused carbon rings, the same family of molecules found in candle soot and interstellar infrared glow, are known to be abundant in space. The galaxy's infrared spectrum flares with their collective fingerprint. But that identification is generic, like knowing a crowd contains people without naming one. No specific aromatic molecule has ever been matched to a specific optical band. Long carbon chains, ionized fullerenes beyond C60, molecules wrapped around metal atoms. Each family has champions and laboratory programs. Meanwhile, the related mystery of the extended red emission, that soft crimson glow from dust across the sky, and the unidentified infrared bands form, with the diffuse bands, a triptych of unread carbon chemistry, possibly 3 views of the same hidden molecular kingdom. One biographical note belongs in this file. Mary Leah Heger did not vanish from astronomy after those plates. She married the astronomer Donald Shane, who would direct Lick Observatory, and as Mary Leah Shane, she became the keeper of the observatory's history. The Lick archives today bear her name. She catalogued the papers of the place where, as a student, she had photographed 2 lines that would not move. There is no record that she considered the bands her mystery. She simply logged them honestly and moved on, which is how most great mysteries enter the record, not with trumpets, but with a careful notation by someone doing their job well. A century later, the notation stands, and the sky has added 548 more lines beneath it. What can be said about the culprits is circumstantial but consistent. The band's widths and shapes suggest large molecules in the gas phase, probably big carbon-based structures, rings and chains and cages, tumbling freely in the cold. Their family groupings, sharpened by recent statistical work that traced new correlated families around Hoag's original pair, suggest dozens to hundreds of distinct species with related chemistry. Taken together, the bands imply something genuinely enormous. Interstellar space is not a sterile vacuum, but a dilute ocean of complex, carbon-rich chemistry. Thousands of trillions of tons of large organic molecules threaded through the galaxy, none of which we can yet name. The same family of chemistry, it is worth saying plainly, from which the precursors of life are drawn. There is even a companion mystery, the extended red emission, a soft crimson glow given off by dust in nebulae across the sky, whose carrier is likewise identified. The galaxy is written in an alphabet we have not learned, in more than one script. I want to pause on the human shape of this one, because it is unusual. Mary Leah Hager noted her 2 stationary lines in 1919 as a student. She lived a long life. She died in 1983, 64 years after those plates, and the lines outlived her, unexplained. They have now outlived nearly everyone who ever worked on them. The diffuse interstellar bands have been handed down through 5 generations of astronomers, each generation refining the catalogue, eliminating candidates, building better instruments, and passing the mystery forward, essentially intact. There is a kind of quiet dignity in that relay. Science is often told as a story of solutions. It is just as truly a story of well-kept questions, carried carefully across a century by people who knew they would probably not live to see the answer. So the next time you see a clear night sky, consider what is actually in the light. Every beam of starlight reaching your eye has crossed hundreds or thousands of light-years of space that is not empty, and has paid a small toll of color to substances no chemist on Earth can name. The oldest cold case in astronomy is not locked in an archive. It is falling on you, gently, every clear night of your life. From light, the universe declines to translate. We turn to a light that may be a message from the very first stars, if it was ever really there at all. Between the release of the Big Bang's afterglow and the ignition of the first stars, the universe passed through an era astronomers call the Cosmic Dark Ages, 100-odd million years with no light sources at all, only cooling gas and gathering gravity. The first stars ended that darkness, and in principle they left a receipt. Neutral hydrogen, which filled the universe, absorbs and emits radio waves at a wavelength of 21 centimeters. When the first starlight woke the hydrogen, the gas should have begun absorbing the background radio glow at that wavelength. A dip, a shallow trough, imprinted on the sky-averaged radio spectrum, stretched by cosmic expansion to lower frequencies. Find that trough, and you have found the fingerprint of the first sunrise in the history of the universe. In February of 2018, a team led by Judd Bowman of Arizona State University announced they had found it. Their instrument, called EDGES, sat in the radio quiet of the Murchison region of Western Australia, and it was almost defiantly modest, an antenna about the size of a dining table, on a metal ground plane in the desert, patiently averaging the radio sky for years. In its spectrum, centered near 78 megahertz, was an absorption trough corresponding to hydrogen roughly 180 million years after the Big Bang. The frequency was right. The shape was plausible. The astonishment was the depth. The trough was about 0.5 degree Kelvin, at least twice as strong as the maximum that standard cosmology can produce. Not a modest anomaly at the margin of error. Twice the permitted value in the first measurement ever made of this signal. If that depth is real, something fundamental is missing from our picture of the early universe, and there are two known ways to supply it. The first, the primordial hydrogen was far colder than physics allows. The gas's temperature at that era is set by well-understood expansion and cooling. To double the absorption, something must have refrigerated the gas below that floor. Within weeks of the announcement, the cosmologist Renan Barkana published the leading candidate, dark matter particles colliding gently with hydrogen atoms and siphoning their heat, a direct, non-gravitational interaction between dark matter and ordinary matter, which has never been observed in any laboratory. The second possibility, the absorption is measured against the background radio glow, so perhaps the background itself was stronger than assumed, an extra radio glow, already filling the universe at cosmic dawn. If that phrase sounds familiar, it should. An unexplained excess radio background is precisely what Arcade 2 recorded, decades later in cosmic time, as the space roar. Two anomalies, separated by 13 billion years, that happen to rhyme. The shape of the claimed signal troubles theorists almost as much as its depth. Standard models predict the absorption trough should be a soft, rounded dip, hydrogen easing into absorption as the first starlight spreads, easing out as heating catches up. What Edges reported was nearly rectangular, absorption switching on quickly, holding a flat bottom, and switching off. A flat-bottomed trough demands that the universe's first light sources turned on with remarkable abruptness, everywhere, in near synchrony, or that the analysis has folded some instrumental artifact into a shape nature never made. Even sympathetic cosmologists found the squareness suspicious. Even skeptics concede that if it is an artifact, nobody has yet demonstrated exactly how it forms. The signal is strange in shape, strange in depth, and strange in its refusal to be either confirmed or cleanly executed. If the dark matter reading were ever confirmed, the implications would be difficult to overstate. The interaction it requires, dark matter particles exchanging heat with ordinary atoms, is exactly what 100 underground experiments have sought for decades without success. The Edges trough would mean the encounter happens, but gently, and only under the conditions of the early universe: cold gas, vast times, patient contact. Theorists exploring the idea found it demands an unusual kind of dark matter, a small fraction of it carrying a whisper of electric charge, a millionth of an electron's. That proposal sits uncomfortably with other observations, as bold proposals do. But it is a measure of the claim's stakes. A table-sized antenna in the outback, if vindicated, would have characterized dark matter's personality before any accelerator or mine on Earth managed an introduction. The next act is already under construction, and its venues are wonderfully austere. Reach, in the South African Karoo, uses two antennas of different designs observing the same sky, a built-in cross-examination, so that any real cosmic signal must appear identically in both, while instrumental ghosts betray themselves by differing. And beyond Earth entirely, instrument teams are preparing radiometers for the far side of the Moon, the one location in the inner solar system permanently shielded from every terrestrial transmitter, where the sky at these frequencies is as clean as it has been since before radio existed. It is a fitting escalation. To referee a dispute about the universe's first sunrise, astronomy is preparing to listen from the far side of another world. Either resolution would be historic, which is exactly why the field demanded a second opinion. It arrived in 2022 from an Indian experiment called Saras-3, a radiometer of a completely different design, floated on rafts in the middle of lakes, using the water itself as a clean, uniform ground. Saras-3 looked for the Edges trough and did not find it. Its data disfavor the claimed signal with about 95% confidence. Two careful experiments, two incompatible answers about the first morning of the universe. That is where the case stands tonight, and it has only sharpened since. Joint analyses published in 2025, weighing both datasets together, lean against the existence of the anomalously strong trough, while stopping short of explaining what, in that case, edges actually measured. The suspicion falls on systematics, the subtle electrical behavior of an antenna's ground plane, the calibration of receivers measuring a signal 10,000 times fainter than the foreground noise of our own galaxy. At least one of these two experiments contains an error nobody has found. It is worth being precise about how hard this measurement is. The foreground radio glow of the Milky Way is thousands of times brighter than the whisper both teams are hunting, and every stray reflection must be modeled to parts in 100,000. A new generation of instruments, a project called REACH in the South African Karoo, and proposed radiometers on the far side of the Moon, the quietest radio environment in the inner solar system, is being built to referee. So the fingerprint of the first stars is, for now, a contested exhibit. Perhaps edges caught the best-kept secret yet from the universe's childhood, hydrogen chilled by the touch of dark matter, or lit from behind by a radio glow nobody can source. Perhaps it caught the electrical personality of its own ground plane. The honest label is unresolved, actively disputed, and worth the wait. The first morning of the universe happened exactly once. Reading its receipt correctly is worth a decade of arguing. The next light on our list had the opposite problem. It was not faint, not contested, and not subtle. It erupted in front of the whole world's telescopes, put on the most beautiful show in modern astronomy, and still walked away with its secret. In early January of 2002, an anonymous star in the constellation Monoceros, the unicorn, riding the winter sky just east of Orion, brightened without warning. Within weeks, the object catalogued as V838 Monocerotis had swelled to roughly 1 million times the luminosity of the Sun, briefly ranking among the most luminous stars in the entire Milky Way. Its outer layers ballooned until the star's radius approached 1,500 times the Sun's, a sphere that, placed where the Sun is, would swallow the orbits of Mercury, Venus, Earth, Mars, and Jupiter. For a few weeks, 20,000 light-years away, something the size of a planetary system was shining with the light of 1 million suns. Astronomers reached for the obvious label, a nova, the runaway thermonuclear flash that occurs when a white dwarf accumulates stolen fuel from a companion. But V838 refused the script at every turn. A nova detonates its surface, flings off a shell, and lays bare a small, blisteringly hot core. This star did the opposite. It cooled as it brightened, sliding redder and redder, and when the show ended, it had become one of the coolest supergiants known, a bloated, cherry-red object wrapped in molecules and dust, with no exposed core anywhere. One astronomer summarized it as a star turning itself inside out. Whatever happened in January 2002, it was not a nova, and it was not any recognized category of eruption. Then came the part that made this object famous far beyond astronomy. The flash of the eruption raced outward at the speed of light and lit up the star's own past. V838, it turned out, was cocooned in enormous shells of dust it had shed in earlier ages, invisible in the dark. As the pulse of light swept through them, shell after shell flared into visibility. Ride that wavefront for a moment. You are the light itself, a spherical shell of brightness expanding at exactly the speed of light, and the darkness around you is not empty. It is furnished, hung with veils of ancient dust in every direction. Each veil ignites as you touch it, curls of amber and rose blooming out of nothing, a cathedral lit room by a single moving candle. And far behind you, a mirror on a mountain, the Hubble Space Telescope, photographs each stage of your journey, year after year, as the glowing rings spread across the sky. Those Hubble images, taken from 2002 through 2006, are among the most reproduced astronomical photographs ever made. They show what appears to be an expanding shell of matter, seeming to swell faster than light itself. It is an illusion, and an honest one. Nothing is moving but illumination. The dust stands still, the light travels, geometry does the rest. Astronomers used the sweep of the light echo to map, layer by layer, the fossil record of everything the star had shed, a biography written in dust, read by a flash. The geometry of a light echo rewards a moment of patience, because it is one of astronomy's loveliest pieces of applied mathematics. At any given date, the dust we see illuminated is not a simple expanding sphere. It is the set of all points whose combined travel time, star to dust, dust to Earth, equals the time since the eruption. That surface is a paraboloid, a hollow bowl opening toward us, sweeping backward through the dust field as the years pass. Astronomers used this relentlessly. The way the echo's rings spread and shifted let them triangulate the star's distance at roughly 20,000 light-years, using polarization of the echoed light as a protractor. The eruption, in other words, measured its own distance for us. Few objects have ever cooperated so beautifully in their own investigation while explaining so little of themselves. The eruption's light curve deserves its own line in the file, because it is a large part of why models keep failing. V838 did not rise and fall. It rose, dipped, rose again higher, dipped, and rose a third time, 3 distinct peaks across roughly 2 months, as if the event happened in installments. A single star swallowing a single companion has no obvious reason to strike 3 blows. Modelers have proposed a grazing first contact, then deeper plunges, or a companion torn into pieces consumed in sequence, or pulses driven by the swollen envelope's own instabilities. Each account handles the peaks and fumbles something else, the energy, the coolness, the speed of the swelling. The event reads less like a single catastrophe than like a short, violent story with chapters, and we were not given the table of contents. What remains on site today keeps the case warm. The star sits swaddled in the dust of its own event, radiating mostly in the infrared, still enormous, still cool, an L-type supergiant, a spectral class so cold and rare that only a handful are known, several of them suspected merger remnants like this one. Its hot blue companion star, after vanishing behind the ejected dust for years, has been glimpsed again as the debris thins. Radio and millimeter observations map molecules condensing in the outflow. Every year of settling tells us more about what the aftermath of such an event looks like, which will matter because population estimates suggest a stellar merger of some scale occurs in our galaxy every few decades. The Milky Way, it appears, does this routinely. V838 is simply the one that happened in front of the cameras, and the cameras, for all they captured, are still waiting for the caption. And after all that, a front row seat, the finest telescopes of the age, a complete light curve, a mapped environment, the cause remains unresolved. The leading hypothesis is a stellar merger, 2 stars in a decaying mutual orbit, spiraling together until they touched, the smaller consumed by the larger in a single catastrophic embrace. The case for mergers as a real phenomenon is strong. A fainter cousin, V1309 Scorpii, erupted in 2008 and was later shown, through years of archival survey photometry, to have been a contact binary whose orbit shrank until the 2 stars became one. That object made stellar mergers observational fact. But V838 itself keeps wriggling free of the details. It has a hot, massive companion star nearby. It sits in a young cluster. Its light curve rose in 3 distinct peaks that no single merger model reproduces cleanly. Its energy budget strains the simplest scenarios. Alternatives survive in the literature. The star swallowing its own giant planets, an exotic internal thermal pulse. 24 years later, The most photographed eruption in history has no agreed explanation. There is a lesson in V838 worth carrying through the rest of this catalogue. Watching something happen is not the same as understanding it. The universe performed this one in full view, with the house lights up, and kept the secret anyway. We stay with dying stars, but we turn now from one that erupted mysteriously to an entire population that may be skipping death's most famous formality. The third part of this catalogue concerns explosions that break the rules, beginning with the explosions that fail to happen at all. Part 3. Explosions that break the rules. A red supergiant is what a massive star becomes in its final act. Having spent millions of years fusing hydrogen, the star swells to hundreds of times its former size, its surface cooling to a sullen ember orange, while deep in its core it burns through heavier and heavier fuels on an accelerating schedule. Betelgeuse, the ruddy shoulder of Orion, is the sky's most familiar example. The textbook ending is famous. The core, having fused its way to iron, can extract no further energy, collapses in less than a second, and the star detonates as a Type II supernova, for a few weeks outshining its entire galaxy. Massive star, red supergiant, supernova. For half a century, that sequence has been a load-bearing wall of astrophysics. Beginning in the late 1990s, astronomers found a way to audit it. Supernovae announce themselves. Galaxies hold still. So when a supernova erupts in a nearby galaxy, researchers, Stephen Smart of Belfast pioneered the method, go back through archival images of that exact patch of sky, taken by the Hubble Space Telescope years before the explosion, and search for the star that died. It is detective work of a satisfying, morbid kind. The explosion provides the death certificate, and the archives provide the portrait of the deceased. Over 2 decades, this method has identified roughly 24 doomed stars in their final years, nearly all of them, as predicted, red supergiants. The audit, however, turned up a discrepancy, formalized in 2009 and known since as the red supergiant problem. Every progenitor star identified in the archives has been comparatively modest, none clearly heavier than about 17 or 18 times the mass of the Sun. Yet the galaxies hosting these explosions visibly contain red supergiants of 25 and even 30 solar masses. Those heavyweights exist. We can point to them, shining in nearby galaxies tonight. They simply never appear in the before pictures of any explosion. The most massive red supergiants are missing from the ledger of deaths. Stars die in our records only up to a certain weight, and above that line, the record falls silent. There is a boring possible explanation, and it deserves its hearing. The sample is small, 24 portraits is not many, and statisticians argue over whether the gap is a 2 sigma fluke or a 3 sigma pattern. Heavier red supergiants also shroud themselves in thick winds of dust, which dims them and can make a heavyweight in an archival image masquerade as a middleweight. Some of the missing mass may be an accounting error written in soot. Careful reanalyses have narrowed these outs considerably, but they have not closed them. And then there is the interesting explanation. Perhaps the heaviest red supergiants do not explode. In the simulations, a supernova is not a guaranteed outcome. The collapsing core launches a shockwave that frequently stalls, and it must be revived, within about a second, by the furious wind of neutrinos pouring out of the newborn neutron star. In many models of the heaviest red supergiants, the revival fails. The shock dies. And then the star, with no explosion to stop it, simply falls. The core becomes a black hole, and the black hole, over hours to months, swallows the rest of the star from the inside. From the outside, modelers predict almost nothing, perhaps a faint, months-long sigh of light as the envelope departs, and then a star that was there is not there anymore. The phenomenon has a name that manages to be both clinical and chilling: a failed supernova. Some astronomers prefer the term unnova. Remarkably, we may have caught one. Since 2008, a survey using the Large Binocular Telescope in Arizona, led by Christopher Kochenek and colleagues at Ohio State, has monitored about 1 million red supergiants across 27 nearby galaxies, checking repeatedly for the opposite of a discovery, a star that stops being there. Their strongest candidate emerged in a galaxy famous for its explosions, NGC 6946, nicknamed the Fireworks Galaxy. One of its red supergiants, about 25 solar masses, brightened weakly across 2009, a flicker consistent with a failing shock's last exhalation, and then faded below every detection threshold and stayed there. No dust cloud fully explains the darkness. Later observations, including with the James Webb Space Telescope, have kept the failed supernova reading alive without certifying it. A star may have died there, with the lights off, while we watched. The physics of the failure deserves a closer look, because it is one of the great unfinished calculations in astrophysics. When a massive star's iron core collapses, it overshoots, rebounds, and launches a shockwave outward through the infalling star, and in essentially every detailed simulation, that shock stalls within milliseconds, strangled by the weight of matter still raining down. What can revive it is the neutrino storm. The newborn neutron star at the center radiates 10 to the 58th power neutrinos in seconds, a number with 58 zeros. And although neutrinos famously ignore matter, the density behind the shock is so extreme that a fraction of 1% of them are absorbed, heating the region like a stove under a stalled pot. Whether the pot boils over, explosion, or the stove loses the race, collapse to a black hole, depends on turbulence, rotation, neutrino physics, and the star's precise inner architecture. The simulations sit balanced on that knife edge to this day. Nature, apparently, sits balanced there too, and the heaviest red supergiants may simply be the ones that fall on the quiet side. The near-solar neighborhood makes the question tactile. Betelgeuse, the ember on Orion's shoulder, the most discussed dying star in the sky, carries an estimated mass right around the danger line, somewhere near 17 to 19 suns. The public conversation about Betelgeuse always assumes its ending will be a spectacle, a supernova bright enough to read by. The red supergiant problem inserts a quieter possibility into that conversation. If the failed supernova reading is correct, and the line sits where the progenitor census suggests, then the sky's most famous doomed star lies close enough to the boundary that its finale is not guaranteed to be a show at all. There is a version of the future in which Betelgeuse, one otherwise ordinary night, simply leaves. A shoulder of Orion gone dim, a constellation quietly edited, and the brightest funeral in the neighborhood cancelled in favor of a private ceremony. There is also a purely observational frontier here, moving fast. The vanished star in the Fireworks Galaxy has been re-examined by the James Webb Space Telescope, and the verdict remains genuinely open. Infrared observations show warm dust at the site, which could be the cooling shroud of a failed supernova's aftermath, or could mean the star survived its outburst and now hides inside a self-made cocoon, an escape artist rather than a corpse. The distinction matters enormously, and it is measurable. A survivor's dust will thin, and the star will re-emerge. A black hole's site will cool toward true darkness. The next decade of monitoring will settle whether we have already watched a star die with the lights off, or only watched one pull the curtains. The phrase to hold on to is this: the missing are as loud as the found. If stars above roughly 18 solar masses routinely collapse in silence, the consequences spread everywhere. It would mean black holes are often born not from the brightest events in the universe, but from the quietest. It would revise the accounting of every heavy element that supernovae are credited with scattering. It would even reshape predictions for the gravitational wave detectors now listening to black holes collide. An absence, in a well-kept ledger, is a measurement. We will meet another such eloquent absence before this part of the night is done. But first, the opposite extreme. Because while the heaviest stars may be dying too quietly, in June of 2015, the universe produced a death so bright it broke the scale entirely. The discovery belongs to one of the most endearing projects in modern astronomy. The All-Sky Automated Survey for Supernovae, inevitably nicknamed Assassin, is a network of small robotic telescopes whose lenses are about 14 centimeters across, comparable to instruments in the hands of serious amateurs. The project's insight was that nobody was watching the whole sky, every night, for bright transients. Fleets of modest lenses could. On June 14, 2015, the network station in Chile flagged a new point of light in an obscure southern galaxy. Follow-up observations, led by the astronomer Subo Dong, revealed that the point of light sat 3.8 billion light-years away, and once the distance was known, the brightness became absurd. At its peak, the object catalogued as Assassin 15LH shone with about 570 billion times the luminosity of the Sun. Set that against the scale of everything around it. Our entire galaxy, several hundred billion stars shining together, emits less. This single point outshone the whole Milky Way roughly 20-fold. It was approximately twice as luminous as the brightest supernova ever recorded before it, an event class that already carried the label superluminous. For weeks, from a single stellar system, poured more light than 20 galaxies produce. The trouble began when astronomers tried to file it. The first folder was the natural one, a superluminous supernova, the death of a giant star inflated to record brightness by a central engine. The favored engine is a magnetar, a newborn neutron star spinning 1,000 times per second, wound with the strongest magnetic fields in the universe, whipping its own rotational energy into the surrounding wreckage. To reproduce this event, that engine must run at essentially its theoretical maximum, every parameter turned to its limit, nothing to spare. Uncomfortable, but not impossible. The genuine problem was the address. Superluminous supernovae come from short-lived giant stars, which live and die in galaxies busy with star formation. This event sat in the serene center of a large, red, retired galaxy, a stellar population that ended its era of building giant stars billions of years ago. It was a young star's death certificate, filed in a retirement community. So a second folder was proposed, and it is stranger. In 2016, a team led by Giorgos Leloudas argued the event was not a supernova at all, but a tidal disruption, a star wandering too close to the supermassive black hole at that galaxy's center and being torn apart by gravity, its remains flaring as they fell in. Several details cooperate. The event sits precisely at the galaxy's nucleus. Its temperature evolution, unusual for a supernova, matches disruption flares. It re-brightened in the ultraviolet in a peculiar double-peaked pattern, and the surrounding gas glows with the highly ionized elements such flares produce. But this folder has its own serious problem. The black hole in that galaxy weighs several 100 million suns, and a black hole that large should not produce a visible disruption at all. Its event horizon is wider than the point at which a sun-like star would be shredded, meaning the star should be swallowed whole, intact and silent, leaving nothing to see. There is one escape clause, and it is spectacular. If the black hole spins at close to the maximum rate general relativity permits, the geometry of its gravity changes, the shredding zone moves outside the horizon, and the flare becomes possible. In that reading, this record-setting light is the signature of a Kerr black hole, a billion-sun monster rotating near the speed limit of space-time, betraying its spin through the manner of one star's death. The discovery machine behind this record deserves its own appreciation because it represents a philosophy. The all-sky automated survey for supernovae began with a handful of 14-centimeter telephoto lenses on robotic mounts in Hawaii and Chile, hardware, complete, costing less than a luxury car, networked to scan the entire visible sky every couple of nights. The bet was that coverage beats aperture. The great observatories see deeply but narrowly, and the sky's rarest events happen where nobody is pointed. The bet paid off within 2 years. The most luminous transient ever recorded was caught not by a billion-dollar flagship, but by the astronomical equivalent of a fleet of camera lenses, because the fleet was looking everywhere at once. Since then, the network has grown to dozens of units on multiple continents, and it has repeatedly demonstrated the same lesson this catalogue keeps teaching. The universe's strangest offerings go to whoever watches widest. The follow-up chronology shows how quickly wonder turned to confusion. The discovery image showed only a bright dot in an anonymous field. A spectrum taken days later at Las Campanas revealed the redshift, and with it the distance, 3.8 billion light-years, which converted a routine transient into an absolute magnitude -23.5 event, brighter than most quasars. For weeks its temperature climbed when supernovae cool, its ultraviolet output surged when supernovae fade, and after about 90 days it re-brightened in the ultraviolet entirely, the double peak that no standard explosion reproduces. Observers threw the full toolkit at it. Hubble localized it to its galaxy's nucleus within a few hundred light-years. X-ray telescopes caught only whispers. Polarimetry, spectroscopy, and years of late-time monitoring all fed a literature that now runs to hundreds of papers. Rarely has one object been so thoroughly measured to so little consensus. What would settle it is known, and mostly requires patience. If events like this are tidal disruptions by rapidly spinning giant black holes, they should recur across the sky at a calculable rate, always in massive quiescent galaxies, always at the nucleus, and the new generation of survey telescopes should harvest a family of them within the decade. If instead they are the extreme tail of magnetar-powered supernovae, their hosts should occasionally be star-forming galaxies, and late-time observations should eventually show the expanding wreckage of a shredded star. Each new specimen will vote. Assassin 15 LH currently stands as a category of 1, and categories of 1 are the universe's way of telling us the filing system, not the object, is what needs work. A decade on, the folders both remain open. The brightest transient of its era was either the most extreme supernova ever recorded, exploding where no such star should exist, or the first object whose sheer visibility measures the spin of a giant black hole. At the outer margins, more exotic files linger, gravitational lensing, stranger stellar corpses. Every reading requires something at the edge of the possible. That is the quiet message of Assassin 15 LH. At the top of the energy scale, our categories are provisional, and one flare 3.8 billion light-years away was enough to expose it. That was a mystery of scale. The next is a mystery of age, an explosion witnessed by candlelight through 17th-century telescopes that has now outlasted 3.5 centuries of attempts to name it. On the evening of June 20th, 1670, a Carthusian monk named Père Dom Antelme looked up from the French town of Dijon and noticed a star that had not been there before, glowing below the head of the constellation Cygnus, the Swan. Within days, the great astronomer Johannes Hevelius, observing from Danzig on the Baltic coast, recorded it independently and gave it a location and a name in the language of the day, Nova sub capite Cygni, the new star below the head of the Swan. It reached third magnitude, easy naked-eye visibility, and then faded. The following spring it returned, brighter than before. It flickered up once more in 1672, weakly, and then it vanished from human sight for 300 years. Hevelius's careful records, position, brightness, dates, sat in the archives like a witness statement waiting for a detective. For most of the 20th century, the case seemed closed by default. The 1670 event, catalogued as CK Vulpeculi, was filed as the oldest well-documented nova, a white dwarf star detonating a skin of stolen hydrogen, flaring and settling back down. Novae are well understood, and the multi-year, multi-peaked light curve was unusual but not disqualifying. Then, in the 1980s, radio astronomers finally located the crime scene, a faint, cold nebula at Hevelius's recorded position, and modern instruments began to examine the remains. Almost nothing matched the file. A nova leaves behind a hot white dwarf and a thin shell of hydrogen-rich debris. CK Vulpeculi's remains are an hourglass, two lobes of gas and dust pinched at a dark, cool waste, and the chemistry of that gas is wrong. It is cold, molecular, and rich in the wrong isotopes. The abundance ratios of carbon, nitrogen, and oxygen do not fit surface detonation on a white dwarf. In 2018, observations with the ALMA and NOEMA radio arrays found something extraordinary in the debris: aluminum monofluoride molecules built with aluminum-26, a radioactive isotope with a half-life of 700,000 years. It was the first radioactive molecule ever detected outside our solar system, and its presence is forensic gold. Aluminum-26 is forged deep inside stars, in layers that never see the surface. Finding it scattered through the nebula means the 1670 event did not scorch a star's skin. It disemboweled a star, flinging interior material into space. The molecular inventory of the remnant reads like a deliberate taunt aimed at every classification. Radio telescopes have catalogued dozens of molecular species in that cold hourglass: carbon-bearing, nitrogen-bearing, oxygen-bearing, and the isotope ratios are wrong in a specific, diagnostic way. The carbon comes too rich in its heavier form, carbon-13. The nitrogen is skewed toward nitrogen-15. The mix speaks of material processed through hydrogen-burning layers deep inside a star, and then ejected without passing through the fires of a true supernova. No classical nova produces that cocktail. No supernova leaves so cool and molecular a corpse. The chemistry alone, before any energy accounting, disqualifies the original verdict, and the aluminum-26, radioactive on a 700,000-year clock, proves the ejection is recent in cosmic terms, consistent with the 17th century date the monks and Hevelius wrote down. The witnesses and the isotopes agree. Only the explanation is missing. CK Vulpeculi also holds a small, strange record that deepens its intermediate status. At the revised 10,000 light-year distance, the 1670 event was intrinsically brighter than any classical nova ever reliably recorded, yet it stayed visible to the unaided eye for barely 2 years and never approached the brilliance a supernova would have shown at that range. A supernova there would have rivaled Venus. The event occupies the energy gap so squarely that modern astronomy has had to invent a shelf for it and its scarce cousins, the intermediate luminosity red transients, a class defined less by what its members are than by what they are not. Several such events have now been caught in other galaxies: red, slow, molecular, dusty, and each time CK Vulpeculi is cited as the possible local prototype. It may be the founding specimen of a whole category of stellar catastrophe that the universe performs regularly and astronomy has only begun to file. And the central object itself, whatever survived, remains unseen. Something at the hourglass's waist still powers the nebula's slow glow, but thick dust hides it from every instrument so far pointed at it. It could be a bloated merger remnant still settling after 3.5 centuries. It could be a compact star wrapped in a debris disk. The James Webb Space Telescope has the infrared reach to pierce that veil, and proposals to try are in the queue. There is a decent chance that within a few years, an instrument launched 350 years after two men logged a new star will finally photograph what their new star became. Whether it will explain them, the record of this catalogue suggests we should promise nothing. Then the case grew again. In 2020, observations sharpened the distance. The object lies roughly 10,000 light-years away, about 3 times farther than long assumed. Distance multiplies luminosity, and at the revised distance, the 1670 explosion released far too much energy to be any nova, while remaining far too faint to be any supernova. It landed squarely in the awkward gap between the two, a luminosity range where classified objects are scarce and understanding is scarcer. The oldest documented nova is not a nova. It is now a founding member of a category without a settled name. The current best story, published in 2024 after detailed modeling of the remnant, is a merger of an odd couple, a bloated red giant star colliding and merging with a small helium white dwarf, the pair spiraling together inside a shared envelope until they became one violently disturbed object. That scenario explains the energy, some of the chemistry, and the hourglass shape. It struggles elsewhere, and the study's own authors, with admirable honesty, catalogued the failures of every published scenario, including their own. An earlier proposal wedded a white dwarf to a brown dwarf. Another invoked an exotic late thermal pulse. Each explains part of the evidence. None explains it all. There is something quietly moving about this one. A monk with his evening sky and an astronomer with a brass telescope and a quill logged an event in 1670 with enough care that 356 years later, a radio array in the Chilean high desert could reopen their case and find a radioactive molecule that proves how strange the event truly was. The observation has been handed across 18 generations, from candlelight to Alma, and the verdict line still reads, "Nature of event unknown." Hevelius did his part. The universe has simply declined, so far, to do its. Old explosions keep their secrets by outliving the witnesses. The final mystery of this part does the opposite. It is brand new, it repeats on a schedule, and it may be the strangest routine behavior any black hole has ever displayed. In December of 2018, the European Space Agency's XMM Newton Space Telescope was pointed at a modestly catalogued galaxy called GSN 069, watching the X-ray glow of the supermassive black hole at its center. Black holes at galactic centers flicker. That is normal. What this one did was not. Roughly every 9 hours, its X-ray brightness leapt by a factor of about 100, a clean, sharp eruption lasting around an hour, and then subsided, and then did it again, and again, on schedule. Astronomers led by Giovanni Minuti announced the discovery in 2019 as something never seen before: quasi-periodic eruptions, a supermassive black hole with what can only be called a pulse. In the years since, the class has grown to roughly a dozen known examples, and the family resemblance is loose in fascinating ways. Some erupt every few hours. One, Swift J0230, erupts roughly every 3 weeks. Some keep steady rhythms, others drift, skipping beats and shifting schedule in ways that resist simple clockwork. All come from the centers of relatively small galaxies, hosting black holes of a few 100,000 to a few million solar masses, lightweights by supermassive standards, cousins in scale to our own Sagittarius A star. And then there is the showpiece. In December 2019, a previously unremarkable galaxy nucleus, about 300 million light-years away, catalogued as SDSS 1335 plus 0728, began, without precedent, to brighten. Astronomers watched an ordinary, quiet galactic center switch on, in real time, for the first time. Then, beginning in February 2024, the awakened nucleus started erupting in X-rays, and its eruptions dwarf every other known example. The object, nicknamed ANSKY, flares roughly every 4.5 days, each eruption roughly 10 times more energetic than a typical quasi-periodic eruption, with a slower rhythm, about 25 days, superimposed on the 4.5-day beat, like a pulse inside a tide. We are not studying an old phenomenon here. We are watching a massive black hole wake up and develop a heartbeat, live, with the entire fleet of X-ray telescopes in attendance. The rhythms themselves carry fingerprints that any final theory must match, and they are wonderfully specific. GSN 69, the founding case, does not simply erupt every 9 hours. It alternates, a slightly longer gap, then a slightly shorter one, then longer again, with stronger eruptions following the long gaps. That alternation is precisely what an orbiting body punching through a disk would produce if its orbit is eccentric and the disk is not perfectly centered. The two crossings per orbit come unevenly spaced, and the deeper plunge makes the bigger splash. Other systems drift in phase, skip eruptions entirely, or shut down and resume. One well-studied case fell silent for 2 years and then restarted, as if the disk it punches through had dispersed and been rebuilt. A star's orbit does not vanish. A disk can. The on-off behavior is, quietly, one of the strongest hints that 2 ingredients are required: a persistent orbiter and a consumable disk. A second thread ties the phenomenon to a process this catalogue's genre knows well: the tidal disruption of stars. Several eruption sources sit in galaxies whose nuclei flared years earlier in exactly the manner of a star being shredded. And in 2024, astronomers monitoring the aftermath of one well-documented disruption watched quasi-periodic eruptions switch on in the debris, roughly 4 years after the star was torn apart. The sequence suggests an assembly line. A black hole destroys one star, builds a temporary disk from its remains, and a second surviving orbiter, perhaps a star that once partnered the victim, perhaps an old stellar remnant on a tightening orbit, then drums through that debris on every pass. If that picture holds, quasi-periodic eruptions are the percussion section of a 2-victim process, and each system we find is a nucleus caught mid-meal with a witness in orbit. The stakes extend beyond taxonomy into the gravitational wave future. If the orbiters are compact objects spiraling inward, each system is a countdown clock. The orbits should decay measurably over years to decades, the eruption intervals shortening on a schedule general relativity specifies exactly. Timing campaigns are already hunting that predicted drift, and early claims of period changes are appearing. Confirm it, and these X-ray drums become the electromagnetic preview of signals the space-based detector LISA will one day hear directly, the same systems announced first in light, later in space-time. Astronomy would then possess something unprecedented, a population of extreme gravity laboratories discovered by their punctuality, each one rehearsing, eruption by eruption, the final music of an object falling into a supermassive black hole. A word about the machinery of this hunt, because the phenomenon's future depends on it. Quasi-periodic eruptions live exclusively in X-rays, and X-ray astronomy is a fleet operation. XMM Newton and Chandra, both flying since 1999, provide the long stares. The Erosita survey instrument swept the whole X-ray sky repeatedly and flushed new eruption sources out of the statistical grass, and smaller, nimbler instruments, including one mounted on the International Space Station, can check a source's pulse on short notice. The discovery workflow has become almost medical. A survey flags an unusual nucleus. The fleet schedules follow-up, and somewhere a graduate student watches a light curve build in real time, hour by hour, waiting to see whether the next eruption arrives on schedule. Several of the field's key results have hinged on observing runs where the eruption simply failed to show, an absence once again carrying as much information as a detection. The sample grows by a few objects per year. Every model currently alive makes predictions about what the next dozen discoveries must look like. The next dozen discoveries are, therefore, already funded, scheduled, and quietly feared by every theorist with a favorite. And it is worth marking what a strange gift this phenomenon is to physics, arriving unbidden in the 21st century's third decade. General relativity's most extreme regime, matter navigating the warped spacetime within a few gravitational radii of a supermassive black hole, was supposed to remain the province of theory and of painstaking one-off observations. Then the universe revealed that some black holes ring like struck bells, on schedules of hours to days, repeatedly, for years, natural experiments that rerun themselves, free of charge, with each eruption sampling the same extreme geometry again. Systems like these are how the orbital mechanics of black hole disks will be measured in practice, not from single catastrophes which never repeat, but from drumbeats which do. If the orbiting body picture holds, astronomers of the 2030s will be timing these systems the way pulsar astronomers time their clocks today, and the quasi-periodic eruptions, mysterious now, will have become precision instruments, the metronomes of strong gravity. What drives the beat? The leading model is wonderfully concrete. Something orbits there. A star, or the dense corpse of one, circles the black hole on a tilted path that carries it crashing through the black hole's disk of hot gas, twice per orbit, once from each side. Each passage punches a hole through the disk and drives out a plume of shocked, radiating gas, an eruption, on schedule, forever, until the orbit decays. If that picture is right, quasi-periodic eruptions are a preview of one of the most anticipated phenomena in physics, extreme mass ratio in spirals, small objects spiraling into giant black holes, which the planned space-based Gravitational Wave Observatory LISA is being built to here in the 2030s. The X-rays would be the visible flag of a system that space-time itself will later sing about. But rival models survive. Instabilities in the disk itself, tearing and reforming on quasi-regular cycles, pairs of interacting remnants, resonances not yet imagined. Ansky, in particular, fits none of the models comfortably. Its energies are too large, its rhythms too layered. The honest label here is unsolved and young. This entire phenomenon was unknown when this century began its third decade. Every few months, a new telescope pointing adds a data point that reshapes the theories. There is a special pleasure in a mystery like this one, not a cold case, but a case still warm, with the universe actively adding evidence while we watch. Whatever the engine is, one sentence is already secure. The universe still debuts new phenomena, on human timescales, in front of working instruments. The catalogue of what exists is not closed. We have now spent an hour and more among distant signals and distant deaths. It is time to come home, most of the way at least. The fourth part of this catalogue concerns the centre of our own galaxy, 26,000 light-years away, our own downtown, decorated and misbehaving in ways nobody has explained. Part 4. The Heart of the Milky Way. In 1984, the astronomer Farhad Yousefzadeh, working with Mark Morris and Don Chance, pointed the Very Large Array, the great Y of radio dishes in the New Mexico desert, at the center of the Milky Way, and found something that exists nowhere else in the galaxy. Rising out of the crowded central regions were filaments, immense, slender threads of radio-glowing material, some stretching 150 light-years in length while remaining a fraction of a light-year wide. To put those proportions in hand, imagine a strand of wire 100 meters long and thinner than a human hair, hanging in a windstorm without bending. The filaments stand mostly perpendicular to the plane of the galaxy, like kelp rising from a seafloor, and their radiolight is synchrotron emission, the unmistakable glow of electrons spiraling along magnetic field lines at nearly the speed of light. They are, in effect, glowing magnetic field lines, drawn across the sky at enormous scale. For nearly 40 years, astronomers knew of a few dozen and understood the origin of none. Then, in 2022, the Meerkat radio array in South Africa, 64 linked dishes in the Karoo, released a mosaic of the galactic center assembled from 200 hours of observation, an image of such depth and clarity that it recalibrated the entire question. The filament count rose from dozens to nearly 1,000. Stand there for a moment, in imagination, in the central 100 light-years of our galaxy. The sky is crowded beyond anything Earth offers. Where our neighborhood holds one star in a volume, the core holds 100,000, and the night there never approaches darkness. And rising through that impossible starfield are the curtains, thin, glowing threads, taller than the distance between the sun and every star you have ever seen with your naked eye, hanging in ordered arrays, humming at frequencies your eyes cannot register, but a radio dish reads as brilliance. Some hang alone. Many hang in pairs and bundles. And here is the detail that no theory has domesticated. In places they hang in evenly spaced parallel sets, like the strings of a harp, spacing so regular that when the images were first examined, the pattern looked less like weather and more like architecture. Nobody knows what builds them. The mechanism must accelerate electrons to relativistic speeds and confine them in threads of magnetic field 150 light-years long. It must do it near the galactic center and nowhere else, and it must produce harp-string regularity as a matter of course. Candidate stories exist, a wind of cosmic rays blowing out of the center and combing the region's unusually strong magnetic field into strands. Old supernova shells stretched and shredded, magnetic flux tubes anchored in the turbulence below. Each explains some filaments. None explains the ensemble, and none explains the spacing. Youssef Zadeh, 4 decades into the problem he opened as a young researcher, has summarized the situation with a candor worth honoring. Every time a question is answered, several new ones arrive. His career is a portrait of a particular scientific virtue, the patience to keep mapping, faithfully and precisely, a structure that declines to explain itself. The map is now 1,000 threads long. The tune remains unwritten. The physical conditions inside the filaments sharpen the mystery considerably. Measurements of their radio polarization show the magnetic fields within them are ordered and strong by interstellar standards, around a milligauss, hundreds of times the galaxy's ambient field, and aligned along each filament's length, like current in a wire. The electrons lighting them are moving at nearly the speed of light, and here is the awkward arithmetic. Such electrons radiate away their energy quickly, in tens of thousands of years, far less time than light needs to travel a long filament's length. Either something reaccelerates the electrons continuously along the entire thread, or the threads are being fed fresh particles from ongoing injection sites. A structure 150 light-years long that must be re-energized everywhere, always, is not a fossil. It is an appliance, plugged into a power source we have not located. The statistical work enabled by the Meerkat harvest has begun to draw the outlines of that power source. With nearly 1,000 filaments to measure, the team could ask population questions for the first time. The vertical threads cluster toward the galactic center. Their brightness declines with distance from it. Their orientations are too orderly for random turbulence. The distribution reads like debris in a current, as if an outflow from the central regions, past or ongoing, streams through the zone and lights or shapes the threads. The 2023 discovery of the horizontal radial spokes strengthened that reading, since spokes pointing at Sagittarius A star practically sign the black hole's name. But correlation is not mechanism. What, exactly, in an outflow builds threads of such uniform thinness? Why harp string spacing, in some sets, as regular as a musical instrument's? Plasma physics offers candidate instabilities that space experiments cannot reproduce and simulations only partially capture. The filaments may be teaching us plasma physics that no laboratory on Earth can reach, a regime of magnetized, relativistic matter at scales no fusion device will ever touch. One comparison puts the strangeness in its frame. Radio filaments resembling these have now been spotted in a handful of other galaxies and in galaxy clusters, longer, fatter cousins trailing from radio galaxies' jets. But nothing found anywhere matches the galactic center population's combination, so many, so thin, so ordered, so local to one galactic nucleus. Our galaxy's downtown appears to manufacture a specific decoration that other downtowns mostly do not, either because the conditions are rare or because only here are we close enough to see them. Every improvement in imaging has multiplied the count. The honest expectation is that the next instrument will do it again, and the harp will grow more strings before anyone names the harpist. And in 2023, the same team found a second population. Scattered through the region are hundreds of shorter filaments lying horizontally, parallel to the galactic plane rather than perpendicular, and arranged radially, like spokes, pointing back toward one address, Sagittarius A star, the 4 million solar mass black hole at the exact center. These horizontal threads glow thermally, differently from the vertical strings, and their geometry suggests they are debris aligned by an outflow, something the black hole did, plausibly within the last few million years, that combed the surrounding material into spokes. Two families of filaments, two different physics, one shared refusal to be explained, and the second family points its collective finger directly at the black hole. Keep that pointing finger in mind, because the next two mysteries of this part concern what that same black hole tolerates around itself, and what it apparently did, not long ago, on a scale that beggars belief. Sagittarius A star is, by the standards of its class, a gentle monster. 4 million suns of mass, compressed within an event horizon smaller than Mercury's orbit, currently consuming so little that its glow is a whisper. Around it, in tight, fast orbits, swings a swarm of stars, and among them drifts a small population of objects that should not have survived the last decade. They are called, with deliberate blandness, the G objects. The story begins in 2011, when a team led by Stefan Gillison identified a faint reddish smudge, catalogued G2, on a plunging orbit aimed almost directly at the black hole. Spectroscopy said gas. The object glowed like a cloud of hydrogen a few times the mass of the Earth. And a gas cloud on that trajectory has a certain future. In 2014, G2 would sweep within about 20 billion kilometers of Sagittarius A star, close enough that the black hole's tides, the difference in gravitational pull between the cloud's near and far sides, would stretch it into a streamer and feed it in. Telescopes across the world scheduled time. Astronomers spoke openly of watching a black hole eat, live, with the meal's arrival date circled on the calendar. The meal never happened. G2 swung through its closest approach, stretched noticeably, and survived. It pulled itself back together on the far side and continued along its orbit, dusty, intact, and unbothered, like a commuter who had walked through a hurricane. A pure gas cloud cannot do that. Tides do not negotiate. Whatever G2 is, it holds itself together with its own gravity. It merely dresses like a cloud. In 2020, Anna Churlo, Andrea Ghez, and the UCLA Galactic Center Group published 13 years of infrared data from the Keck telescopes, doubling the census, 6G objects on 6 different orbits, ranging from about 100 to 1,000 years, all sharing the same contradiction: the look of gas, the durability of stars. Ghez shared that year's Nobel Prize in Physics for the decades of orbital tracking that made such a census possible at all. The leading explanation for her strange menagerie is elegant. Each G object may be a pair of stars that the black hole itself forced together. In the crowded center, binary stars orbiting close to Sagittarius A star have their orbits relentlessly perturbed by its tides, and calculations show many should be driven to collide and merge. A freshly merged star is a mess, bloated, unsettled, cocooned in the debris of its own union for roughly 1 million years before it calms into an ordinary-looking single star. Bloated, dusty, self-gravitating, precisely the G object profile. If the hypothesis is right, we are looking at a production line. The black hole manufactures merged stars as a routine byproduct of its own gravity, and the G objects are the fresh inventory, still in their packaging. The setting for this mystery deserves a fuller portrait, because context is what makes the G object's survival so implausible. The stars nearest Sagittarius A star, the S stars, trace some of the most extreme orbits known to astronomy. The most famous, S2, loops the black hole every 16 years, and at closest approach it moves at nearly 3% of the speed of light, fast enough to cross the continental United States in half a second. Tracking those stars through decades, with adaptive optics telescopes and later the gravity interferometer, is what proved a 4 million solar mass object sits there and earned the 2020 Nobel Prize. The same tracking showed relativity at work in a star's orbit, S2's light measurably reddened by gravity at closest approach, its ellipse slowly pirouetting as Einstein requires. This is the neighborhood the G objects casually commute through, a region where space-time itself is visibly bent, where tides shred the loosely bound, and where a cloud of gas has the life expectancy of a snowball in a furnace. The 2014 encounter was, at the time, one of the most anticipated events in modern astronomy, and its anticlimax taught the field something valuable about its own assumptions. Predictions were published of a feeding event that might brighten Sagittarius A star 100-fold. Some speculated more, as G2's shredded remains rained in. Observing campaigns booked telescopes across every wavelength. What followed was almost comedy. The black hole barely burped. The Great Awakening never came, and G2 sailed on, slightly stretched, entirely alive. It was the most productive non-event in years, because a failed prediction is a measurement. Whatever G2 is, its core is bound by its own gravity at roughly the density of a star, not a cloud. Since then, the monitoring has continued quietly. Orbits refined, dust shells measured, new candidate members proposed, and each of the 6 known G objects will make its own closest approach in the decades ahead. A scheduled series of natural experiments with dates already on the calendar. If the merger product hypothesis is confirmed, the implications reach well past the galactic center. Astronomers increasingly suspect that a meaningful fraction of the galaxy's seemingly single stars are the fused remains of former pairs, and the crowded center, where the black hole's tides squeeze binary orbits relentlessly, should be the galaxy's most productive fusion venue. The G objects would then be the only place in the universe where we can watch the aftermath of stellar mergers as a population, each at a different stage of settling, arranged conveniently around the strongest clock in the galaxy. The black hole would be, in a real sense, running the experiment for us, forcing the mergers, setting the orbits, and holding the results where the finest telescopes on Earth happen already to be pointed. It remains a hypothesis. Rival readings, dense knots in gas streams, evaporating disks around young stars, retain defenders, and the honest label is unsolved. But there is something almost fond in what the data show. The most extreme gravitational environment in the galaxy, home to the strongest tides and the fastest stars, keeps a small collection of objects that walk through the storm unharmed, and our best guess is that the storm made them. The G objects are a mystery of what the black hole spares. The next is a mystery of what it did, because our gentle monster, it turns out, has a recent and violent past, and the receipts are larger than the galaxy itself. In 2010, 3 researchers, Meng Su, Tracy Slatier, and Douglas Finkbeiner, were mining the public data of the Fermi Gamma Ray Space Telescope when they found something enormous hiding in plain sight. Ballooning out of the center of the Milky Way, one above the galactic plane and one below, were 2 vast lobes of gamma-ray emission, each about 25,000 light-years tall, together spanning half the width of the galaxy itself. Their edges were not the soft gradients of old, diffuse structures. They were sharp, defined, like the skin of a blown bubble. The structures had been overhead through the entire history of astronomy, radiating at energies no human eye or optical telescope registers, and nobody had known. They are called the Fermi Bubbles, after the telescope that finally saw them. A decade later, the picture widened. In 2020, the Rosetta X-ray telescope mapped the whole sky and revealed a second, even larger pair of bubbles, envelopes of hot, X-ray glowing gas extending some 45,000 light-years above and below the plane, wrapping around the gamma-ray lobes like an outer shell around an inner one. The natural reading is that the Rosetta bubbles are the shock front, and the Fermi bubbles the interior of a single titanic event. Add up the energy required to inflate the whole structure, and the number lands around 10 to the 56th power ergs, the output of roughly 100,000 supernovae, delivered as a single sustained exhalation from the center of our galaxy. Something did that. Recently, and we do not know what. The bubbles came with corroborating witnesses that make dismissal impossible. Years before Fermi flew, microwave telescopes had recorded an unexplained haze around the galactic center, a fog of emission with the wrong spectrum for dust or ordinary gas, and X-ray surveys of the 1990s had hinted at vast structures arcing above the plane. When the gamma-ray lobes appeared, the older anomalies snapped into place as pieces of the same anatomy, the microwave haze filling the bubble's lower reaches, the X-ray arcs tracing their walls. Multiple instruments, over 3 decades, had each seen a limb of the same buried giant without recognizing the body. That is worth remembering when this catalogue's other orphan signals come to mind. Some of today's disconnected anomalies are probably limbs of things not yet assembled. The interior of the bubbles has since been probed directly, with a technique of quiet elegance. Distant quasars shine through the bubbles from behind, and their ultraviolet light arrives at Hubble, bearing the absorption fingerprints of gas clouds inside the structures. The Doppler shifts of those fingerprints clock the cloud's motion. Material inside the bubbles is rushing outward at hundreds of kilometers per second, velocities that, run backward, date the launch to a few million years ago, independently corroborating the other clocks. The bubbles are not fossils of some ancient era. They are the still expanding smoke of a recent event, caught mid-drift. Every line of evidence, sharp edges, hot walls, cloud speeds, the lit-up Magellanic Stream, agrees on the timing and disagrees only on the trigger. It is worth being explicitly sleep-safe about what this does and does not mean for anyone under this sky tonight. Even when the central engine last ran at full power, the Earth was never in the line of fire. The outflows vent perpendicular to the galactic plane, straight up and out of the disk, while we sit far out in the suburbs within the plane itself. A future outburst of Sagittarius A star, and on the evidence, there will eventually be one, would be a scientific festival, not a hazard, a few million years of the galaxy's core glowing brighter in wavelengths human eyes cannot see, 26,000 light-years of vacuum away. The bubble's lesson is not danger. It is humility about quiet things. The stillest object in our sky's farthest background has a documented temper, and the interval between its moods is shorter than the lifetime of a species. There are 2 families of suspect. The first is the black hole itself. Sagittarius A star may be quiet now, But black holes are only as calm as their last meal, and several independent lines of evidence suggest ours dined violently within the last few million years. Recent modeling reproduces both bubble pairs with a jet, a focused relativistic outflow from the black hole that switched on roughly 2.6 million years ago and ran for about 100,000 years before shutting down. And there is a separate, remarkable witness. Trailing far below the galaxy's south pole is the Magellanic Stream, a river of gas torn from the Magellanic Clouds. Portions of that stream are glowing, ionized, as if flashlit, and the required flash matches a burst from the galactic center a few million years ago, a searchlight that reached hundreds of thousands of light-years out. Two independent clocks, both pointing at the same recent era. The second family of suspect is collective, not the black hole alone, but the central regions in concert. A burst of massive star formation near the core, thousands of supernovae detonating over a few million years, their combined winds inflating the bubbles from below. This story has its own support in the chemistry and energetics, and a 2025 variant proposes an unsettlingly steady engine, the black hole shredding one star every 10 to 100,000 years, on average, each disruption puffing more hot gas into the growing structure, the bubbles as the accumulated breath of 100 quiet catastrophes. Sit with the timing for a moment, because it is the part that stays with you. 2.6 million years ago is not distant cosmic history. It is the era of the first stone tools. When the ancestors of humanity were learning to knap flint on African floodplains, the center of the galaxy, from their vantage a bright band across the night, may have been running a jet bright enough that, at some wavelengths, it would have outshone the rest of the sky's structure entirely. The bubbles overhead tonight are the fossil of an event that early hominins, in the most literal sense, lived beneath. Our galaxy's core has moods, and the interval between them is shorter than the age of our species. That leaves the obvious question, the one the bubbles ask on their way out. If our black hole was recently loud and is currently quiet, what governs the schedule? The honest answer is that nobody knows, because we cannot yet name the last event, let alone forecast the next. The bubbles are a message from the engine room, still being translated. It is natural to wonder what the bubbles would look like if human eyes could see them, and the answer rearranges one's sense of the night sky. From Earth, the Fermi Bubbles span well over half the sky's height. From horizon toward zenith, a pair of glowing towers rooted in Sagittarius, wider across than 100 full moons placed side by side. They would be by far the largest single structure visible from our planet, dwarfing the Milky Way's band that they erupt from, a permanent architecture of the southern and northern sky, rewriting every culture's constellations. Instead, they radiated energies 1 billion times beyond the eye's reach, and so humanity spent its entire history beneath them, naming star patterns and navigating oceans, without one myth, one legend, one line of scripture recording that the sky wears wings. It is one of this catalogue's most instructive lessons. The sky we see has never been most of the sky. What else hangs overhead at wavelengths we have not yet built eyes for is not a rhetorical question. Every entry in tonight's list argues it deserves a literal answer. And there is one more mystery attached to that engine room, not about what our black hole did, but about its family tree. Because when astronomers count the black holes of the universe, they find the ledger has a hole in the middle. Black holes come, observationally, in two well-stocked sizes. There are the stellar mass black holes, corpses of individual giant stars, ranging from a few solar masses up to around 150. We know them by the dozens from X-ray binaries in our own galaxy, and by the hundreds now from the chirps of their collisions in gravitational wave detectors. And there are the supermassive black holes, hundreds of thousands to tens of billions of solar masses, one anchoring the center of essentially every substantial galaxy, our own 4 million sun specimen included. Between those two populations, from roughly 150 to 100,000 solar masses, lies a desert. The intermediate mass black holes, the entire middle class of the population, are missing. Not rare. Nearly absent. The absence is embarrassing for a simple reason. The middle class must exist, or must have existed. Supermassive black holes cannot be born at 1 million solar masses from any known stellar process. They must grow, and growth passes through the middle. Worse, the growth is on a deadline. Quasars, galaxies lit by feeding billion solar mass black holes, existed less than 1 billion years after the Big Bang. Building a billion-sun black hole from 100 sun seeds in under 1 billion years requires feeding at the theoretical speed limit, continuously, from birth, a schedule so tight that many theorists consider it broken. This is called the seed problem, and the missing middle sits at the center of it. The adolescence of the population, the evidence of how the giants grew, are simply not on file. The candidate file is thin but real. An object called HLX-1, in a galaxy 290 million light-years away, flares in X-rays with a brightness that implies roughly 20,000 solar masses, long the best single candidate, possibly the stripped nucleus of a swallowed dwarf galaxy. Another X-ray source appears to be a middleweight black hole caught shredding a star in a star cluster at a galaxy's edge. The gravitational wave event GW190521, detected in 2019, merged two heavyweight stellar black holes into a remnant of about 142 solar masses, the first confirmed birth of an object inside the desert, though only just across its border. And closest to home, in the great globular cluster Omega Centauri, a swarm of 10 million stars visible to southern hemisphere eyes, 2 decades of Hubble imaging revealed, in 2024, 7 stars near the core moving too fast to stay unless something unseen anchors them, a compact mass of at least 8,200 solar masses. That would be an intermediate black hole 17,000 light-years from Earth, the nearest large black hole of any kind. The rival reading, a tight swarm of many small black holes, has not been eliminated. The same ambiguity haunts every similar cluster candidate. There is a reason the desert's lower border sits near 150 solar masses, and the reason is itself a remarkable piece of physics. Stars above roughly 130 solar masses die differently. Their cores grow so hot that light itself begins converting into electron-positron pairs. The radiation pressure holding the star up abruptly softens, and the star detonates in a pair instability supernova, an explosion so total that nothing remains. No corpse, no black hole, nothing. Theory therefore forbids stellar deaths from minting black holes in a band from roughly 65 to 130 solar masses, and observations of merging black holes have indeed found that range sparse. The heaviest ordinary stellar roots top out well below 200 suns. Above that, the only known assembly methods are second-hand, black holes eating black holes, or stars colliding in runaway pile-ups at the hearts of dense clusters. The desert, in other words, is not an observational accident waiting to be filled by better telescopes. Known physics actively fences its lower edge, which makes every object found inside it a genuine event. That is what made the gravitational wave event of 2019 so consequential. The two black holes that merged, roughly 85 and 66 solar masses, were themselves awkward residents of the forbidden band, hinting they were second-hand products of earlier mergers, and their union built a 142 solar mass remnant, the first object ever observed being deposited inside the desert. It was a birth certificate for the intermediate class, issued by space-time itself. But one certificate does not populate a census, and the desert's upper reaches, thousands to tens of thousands of suns, the masses that could seed giants, remain nearly empty of confirmed residents. The dwarf galaxies offer the most promising hunting ground. Small galaxies that never merged their way to supermassive status should retain their original modest central black holes, and a scattering of candidates in the tens of thousands of solar masses has been catalogued in their nuclei. Each is an heirloom seed, preserved by an uneventful history, if the measurements hold. The connection to everything else in this part of the catalogue is direct. Whichever way the desert resolves, it rewrites the biography of the giants. If patient searches fill the middle, black holes of thousands of suns lurking in globulars and dwarf nuclei, then growth was gradual, and our own galaxy's 4 million sun center is the summit of a long, slow climb, whose base camps we can still visit. If the desert is real and the middle was skipped, then the giants were born giant, in a first billion years process with no modern counterpart, and the only witnesses to that process would be objects like the ones the next part of this catalogue ends with, small, red, and waiting at the edge of the deepest images humanity has ever taken. So the middle class is either hiding or genuinely scarce, and both answers would teach us something large. If intermediate black holes lurk in globular clusters and dwarf galaxy nuclei, patient astrometry will corner them within a generation. If they truly are scarce, then the giants likely skipped the middle entirely, born already heavy, through the direct collapse of enormous primordial gas clouds, a birth channel with no local counterpart. Hold that thought carefully. It is not an orphan idea. In the next part of this catalogue, we will meet a newly discovered population of objects, seen at the dawn of cosmic time, that may be exactly that process, caught in the act. The missing are as loud as the found. Earlier tonight, that phrase belonged to giant stars absent from the ledger of explosions. Here it returns, one octave lower, an entire weight class absent from the ledger of black holes. An absence, mapped carefully enough, becomes a shape, and the shape of this one may be the missing chapter in the biography of every galaxy, including the one over your roof. We have reached, more or less, the midpoint of the catalogue, and it is worth pausing on a hillside to look back at the territory. 15 cases in, notice what has changed as we walked. The mysteries began far away and impersonal, a roar in the radio sky, antimatter dying at the galaxy's heart, and they have been drawing steadily closer to things with addresses, our own galactic center's harp strings and bubbles, the missing relatives of our own central black hole. Notice, too, the recurring shapes. Instruments built to hear one thing keep hearing another. Absences keep proving as loud as discoveries. Every improved eye multiplies the questions it was built to settle. Hold those patterns, because the second half of tonight's walk will bend the path further homeward, through galaxies stranger than ours, then down into our own solar system's tracking data and property lines, and finally into the foundations under everything, where the last mysteries are not in the sky at all, but in the arithmetic. The catalogue's outer wing is behind us. The doors from here on open inward. The fifth part of this catalogue widens the frame to entire galaxies. And it begins with one that looks, in every photograph, like it was drawn with a compass. Part 5. Galaxies that should not exist. In 1950, an American astronomer named Art Hoag was examining photographic survey plates when he came upon an object in the constellation Serpens, so tidy that his first professional instinct was to disbelieve it. What the plate showed, about 600 million light-years away, was a ring, a thin, luminous, almost perfectly circular hoop of light, surrounding a compact, round, yellow ball of stars, with an apparently empty dark gap between the two. It looked less like a galaxy than like a diagram of one. Hoag himself proposed the sensible escape. Perhaps the ring was an illusion, a gravitational lens, the light of a background object bent into a circle by the gravity of the foreground ball. It was a good idea, and it was wrong. Follow-up work ruled lensing out decades ago. The object, known ever since as Hoag's object, is real, a single galaxy, wearing a ring 120,000 light-years across, wider than the Milky Way, made of billions of hot young blue stars, around a core of old yellow ones, with that unexplained moat of darkness in between. Ring-shaped galaxies exist elsewhere, and mostly we understand them. Roughly one galaxy in 1,000 carries some ring-like feature, and the classic route is violence. A small galaxy dives straight through the disk of a larger one, and the impact drives a circular density wave outward, a splash frozen in starlight. The Cartwheel Galaxy is the textbook case, and it shows its history plainly: a disturbed hub, spokes of gas, and the culprit galaxy visible nearby, still fleeing the scene. Hoag's object has none of that. There is no plausible culprit anywhere in the neighborhood. The yellow core's stars move calmly, with none of the kinematic bruising a collision leaves. Radio mapping of the ring's hydrogen shows it rotating in an orderly, settled way, more like an old institution than fresh wreckage. If this ring was made by a crash, the crash has been erased with implausible thoroughness. The alternative explanations each stumble. Perhaps an earlier version of this galaxy had a bar, an elongated spine of stars, common in spirals, that herded gas outward into a ring and then dissolved. But bars form in flat disks, and the core of Hoag's object is not a flattened disk. It is a rounded spheroid that should never have hosted a proper bar. Perhaps the ring is captured material, gas that drifted in along the invisible filaments of the cosmic web billions of years ago and settled quietly into orbit, condensing into stars far from the core. This story fits the calm kinematics and is currently the least rejected option, which is not the same as being confirmed. It amounts to saying the galaxy assembled its own halo of mystery gradually and left no receipts. 75 years after Hoag logged it, there is no consensus on how the cleanest ring in the sky was built. One more detail, almost too neat: through the dark gap between core and ring, in the deep Hubble image, a second, far more distant ring galaxy happens to be visible, a coincidence of alignment, a ring seen through a ring. The universe does not arrange such things on purpose. It simply owns enough galaxies that even its rarest shapes occasionally photobomb one another. The measurements accumulated across 75 years make the missing explanation more embarrassing, not less. The ring's neutral hydrogen has been weighed. Billions of solar masses of gas, ample fuel for the ongoing formation of its young blue stars. The rotation has been clocked at over 200 kilometers per second, smooth and circular, with no measurable disturbance. Spectroscopy of the core finds an old, orderly population of stars rotating in the same plane and direction as the ring, a detail that quietly wounds the collision hypothesis, since a plunging intruder has no obligation to leave core and ring co-rotating so politely. Deep imaging has hunted the field for tidal debris, faint shells, or a disturbed companion galaxy that might be the fled culprit, and found the neighborhood almost aggressively tidy. Every measurement returns the same character reading, "This is not a system recovering from trauma." It is a system that appears to have been built this way, calmly, and that is precisely what no standard channel provides. The timescale argument is the quiet killer of easy stories. A thin ring of gas and stars orbiting a central body is a delicate structure. Left alone, orbital shear and gravitational instabilities should smear or clump it over a few billion years. Yet the stellar populations in the ring imply it has been forming stars steadily for at least a couple of billion years, and the gas reservoir suggests it will continue for billions more. Something either built it recently enough to look fresh, in which case the absence of wreckage is inexplicable, or built it long ago in a configuration stable enough to persist, in which case the assembly was gentler and stranger than any collision. The cold accretion picture, where filaments of intergalactic gas wound themselves into a ring over eons, fits that gentleness, but it demands an unusually clean inflow geometry and an unusually undisturbed host, a galaxy that spent billions of years being left entirely alone. Hoag's object may owe its perfection to cosmic solitude, the rarest luxury in a universe built on collisions. The man who found it deserves a paragraph of his own, because his relationship with the object became one of astronomy's gentler ironies. Art Hoag was no fringe figure. He went on to a distinguished career, directing stellar programs at Kitt Peak National Observatory and serving as president of the Astronomical Society of the Pacific. Yet his most lasting fame attaches to a single paragraph he published in 1950, describing an object he himself suspected was not real. He offered the ring, almost apologetically, as either a peculiar galaxy or a photographic curiosity, and leaned toward doubting it. The universe overruled his modesty. For decades afterward, as instruments improved, each new observation made his curiosity more solid and more inexplicable. Photographs became photometry, photometry became spectroscopy, spectroscopy became radio maps, and at every step the ring refused to resolve into anything ordinary. A scientist's most famous discovery, being one he tried to talk himself out of, is a fitting emblem for this whole catalogue. The universe does not require our confidence to keep its appointments. The object's rarity has since been quantified, and the numbers sharpen its solitude. Surveys suggest that galaxies of Hoag's precise type, a detached, luminous, star-forming ring around an undisturbed round core, with no bar and no visible perturber, number perhaps 1 in tens of thousands. A scattering of partial lookalikes has been catalogued, informally called Hoag-type galaxies, but examined closely, nearly all of them cheat, a faint bar lurking in the core, a smeared spiral pattern masquerading as a ring, a disturbed companion loitering nearby. The clean cases can be counted without running out of fingers. Whatever assembled Hoag's object is either an extraordinarily rare accident, a once-per-million galaxy's convergence of gentle circumstances, or a process that operates commonly but leaves this visible signature only when every disturbance stays away for billions of years. Either reading makes the ring precious. It is a control experiment the universe ran for us, a demonstration of what patient gravity builds when absolutely nothing interferes. Hoag's object earns its place in this catalogue as a reminder that mystery does not require exotic physics. Every ingredient here is ordinary: stars, gas, gravity. Only the arrangement is inexplicable. Some structures survive by erasing their own history, and this one has kept its silence for at least a few billion years. A galaxy with an impossible shape is one kind of puzzle. The next galaxies on our list have an impossible inventory. They are missing the one ingredient that galaxies are, by every modern account, built from. To feel the weight of this next mystery, you need one background fact. For half a century, the evidence has said that every galaxy is embedded in a halo of dark matter, invisible, intangible material, detectable only by gravity, outweighing the visible stars several times over. Galaxies do not merely contain dark matter. Galaxies exist because dark matter's gravity gathered the gas that became their stars. It is the scaffolding, the foundation, the load-bearing frame. Every rotation curve of every normal galaxy testifies to it. Which is why, in 2018, a short paper about one faint smudge in the constellation Cetus landed like a dropped plate. The smudge is called NGC 1052 DF2, a large, dim, ghostly galaxy of the kind called ultra-diffuse, about the Milky Way's width, but with 1/100th of its stars, so sparse you can see other galaxies through it. Peter van Dokkum of Yale and his colleagues found it with an instrument that sounds like a joke and is not, the Dragonfly Telephoto Array, a rack of high-end camera lenses in New Mexico, purpose-built to see faint, fluffy things professional telescopes overlook. To weigh the galaxy, The team clocked the speeds of its globular clusters, bright knots of stars orbiting within it. In a normal galaxy of that size, dark matter's gravity would swing them at 30 or 40 kilometers per second. The measured spread was about 8. Do the arithmetic, and the total mass comes out approximately equal to the mass of the visible stars alone. Nothing left over. A galaxy with no meaningful dark matter, the astronomical equivalent of finding a skyscraper with no steel frame, standing anyway. The claim drew immediate, ferocious challenge, most of it aimed at distance. If DF2 were closer than claimed, its stars would account for more of its mass, and the anomaly would soften into normality. The dispute ran for years and was settled by the sharpest ruler available, the tip of the red giant branch, a standard brightness that stars reach at a known stage. Verdict: roughly 65 million light-years. The galaxy is far, the arithmetic stands, and meanwhile its neighbor DF4 was shown, in 2019, to share the same condition. Two ghosts, missing their frames. Then the case turned from anomaly to detective story. The two galaxies share a second oddity. Their globular clusters are freakishly luminous, roughly twice as bright as the universe's standard issue, as if whatever made these galaxies also supercharged their clusters. And they are not alone. They sit within a striking line, a trail of faint galaxies strung across the NGC 1052 field, with velocities ordered along it like beads sliding on a wire. In 2022, Van Dokkum proposed a reconstruction of the crime, the bullet dwarf collision. Some 8 to 9 billion years ago, two gas-rich dwarf galaxies collided head-on. Their dark matter, which interacts with nothing, passed through the collision untouched and sailed on into the dark. Their gas, which does collide, slammed, stopped, and was left behind at the crash site, where it condensed into a string of new galaxies built from gas alone, born without frames, their infernal early star formation forging the overbright clusters. The model made a testable prediction: the trail should hold more such galaxies, and the universe has been cooperating. A third dark matter-deficient member of the trail was confirmed in 2026, and a similar object has turned up in the Fornax cluster, suggesting the species is not unique to one accident site. The observational campaign behind this mystery is a small epic of modern astronomy worth telling on its own. Measuring the internal motions of a galaxy this faint pushes instruments to their limits. The team needed the world's largest optical telescopes just to clock 10 globular clusters drifting at bicycle race speeds around a galaxy 100 times dimmer than the night sky's own glow. The distance war that followed consumed years and dozens of telescope nights. Rival groups measuring the brightness of the galaxy's reddest giant stars, a standard candle stage of stellar old age, arriving at first at answers different enough to decide the whole question. The dispute was settled the expensive way: 40 orbits of Hubble time devoted to one faint smudge, yielding a distance near 72 million light-years and cementing the anomaly. It is worth absorbing that price tag. A single ghostly galaxy, invisible to every survey until this decade, commanded one of humanity's premier instruments for weeks, because if its arithmetic held, a foundation stone of galaxy formation needed reinspection. The arithmetic held. The bullet dwarf reconstruction, if it continues to survive testing, would be quietly historic for a second reason. It would be a small-scale replay of the most famous dark matter evidence ever collected. In the Great Bullet Cluster, two colliding galaxy clusters showed their hot gas slammed to a halt at the crash site, while their dark matter, mapped by gravitational lensing, sailed cleanly through and beyond. That separation of substance from scaffold made the case for many that dark matter is a thing rather than a law. The trail of galaxies behind DF2 and DF4 would be the same experiment run by nature at 1,000th the scale, with the poignant twist that here, the stranded gas went on to become galaxies, orphan systems built entirely from the collision's leftovers, condemned to live without the frames their parents kept. Cosmology rarely offers second, independent stagings of its landmark demonstrations. This may be one, still being excavated. Fairness requires recording the survivors' defense. Advocates of modified gravity note their theory contains a subtle escape. A small galaxy sitting in the gravitational field of a large neighbor behaves differently than one in isolation. The external field can suppress the extra gravity, making a satellite look dark matter-free without being special. DF2 and DF4 do sit near the big galaxy NGC 1052, so the escape is at least available. The rebuttal, kinematically similar diffuse galaxies in comparably strong external fields, show normal dark signatures, and the trail's coherent geometry fits an accident of history better than a field effect. The debate continues at conference volume rather than crisis volume, but it is live, and honest bookkeeping keeps it on the record. Whichever side wins, these ghosts have already performed their service. They turned dark matter from an assumption into a variable, and forced every theory to explain not just its presence, but its occasional, spectacular absence. Now hold this mystery up to the light, because it has a beautiful twist. Galaxies missing dark matter are, counterintuitively, an argument for dark matter. The rival school of thought, modified gravity, holds that there is no invisible substance. Instead, gravity itself strengthens where matter is sparse, mimicking a halo. But if extra gravity is a law of nature, it must apply everywhere, to every galaxy equally. It cannot be present in Dragonfly 44, an ultra-diffuse galaxy of the same class whose stars move so fast it appears to be almost entirely dark matter, and absent in DF2 and DF4. A substance can be stolen, stripped, or left behind by an accident of history. A law of nature cannot. These faint ghosts, in other words, testify that the invisible scaffolding of galaxies is a separable thing, present here, absent there, portable, thievable. We still do not know what dark matter is, but a handful of see-through galaxies have quietly told us something about what it is like. The honest label, contested in its details, alive in its implications, and moving fast. And for completeness, one adjacent open wound in the same theory, in a single sentence. The satellite galaxies of both the Milky Way and Andromeda orbit, preferentially in thin, coordinated planes, where standard cosmology expects disordered swarms, a separate, stubborn misbehavior at galactic scales that remains unexplained. And now the anchor of this part. Because when humanity finally launched the greatest telescope it had ever built and pointed it at the first billion years of cosmic time, the universe marked the occasion in characteristic style. It showed us something that matches nothing in the catalogue. The James Webb Space Telescope opened its eye in the summer of 2022, and its founding assignment was time travel, to look so far away, and therefore so far back, that it could watch the universe's first galaxies assembling. It has done that assignment magnificently. But scattered through its first deep images, astronomers kept noticing something off-script. Tiny, faint points of light, unresolved or nearly so, colored a strange, insistent red. Not a few of them. Hundreds. They clustered in cosmic time between roughly 600 million and 1.5 billion years after the Big Bang, and they matched no known category of object. The discovery papers reached for gravity and dignity and settled, in the end, on the name that stuck, the little red dots. Everything measurable about them is contradictory. They are almost absurdly compact. Their light comes from regions only a few hundred light-years across, thousands of times smaller in volume than the Milky Way, yet they shine with the output of small galaxies. Their spectra have a peculiar V-shape, blue in the ultraviolet, then pivoting abruptly to red in the optical, as if two different objects were stapled together. Many show broad emission lines of hydrogen, the classic signature of gas swirling at thousands of kilometers per second around a massive central object. That last clue would ordinarily close the case. Gas moving that fast, that centrally, means a feeding supermassive black hole, a small quasar. But the little red dots refuse the quasar badge too, and they refuse it 4 separate ways. Feeding black holes blaze in X-rays. The dots are almost X-ray silent. Quasars flicker. The dots hold eerily steady. Quasars glow in radio. The dots do not. Feeding black holes warm their surrounding dust until it shines in the infrared. The dots show no such warmth. Every calling card a black hole ordinarily leaves is missing. And if you try the other identity, no black hole, just stars, the arithmetic turns hostile. Packing enough stars into a few hundred light-years to produce that light requires stellar densities without precedent anywhere in the observed universe, and enough such objects existed at cosmic dawn that early estimates briefly threatened the galaxy formation budget of standard cosmology itself. The early nickname for that scare, universe breakers, faded as measurements improved, but the core tension held. As galaxies, the dots are too much, too small, too early. As quasars, they are too quiet. They are a population of objects, in the hundreds, that fails both available identities. One more property sharpens the strangeness. They are creatures of a particular era. Abundant at cosmic dawn, they thin out drastically by 1.5 billion years after the Big Bang and essentially vanish from later cosmic history. Whatever they are a phase, something the young universe did once and then stopped doing. The hypothesis now gathering evidence, and this mystery is being actively cornered as you listen, so I will label each piece honestly, is that the little red dots are something astronomy has never had in its catalogue before: black hole stars. Picture a supermassive black hole, thousands to millions of solar masses, in its infancy, not naked as quasars are, but buried inside a dense, turbulent envelope of hydrogen gas, an atmosphere thousands of light-years smaller than a galaxy, but enormously heavier than any star. The black hole feeds furiously at the center. The envelope swallows the X-rays, smooths out the flickering, and re-radiates the fury as the soft, steady, reddened glow of a single monstrous star-like surface. Not a star powered by fusion, a star-shaped object powered by a black hole's appetite. The concept sounds like science fiction, and it accounts, one by one, for every contradiction on the list: the compactness, the steadiness, the silence in X-rays and radio, the V-shaped spectrum. The supporting evidence has been arriving in quick succession. One dot, nicknamed the Cliff, shows a spectral break so sharp that ordinary stellar populations cannot produce it, while a dense cocoon of gas around a feeding black hole reproduces it well. Another, examined in depth in 2025 and 2026, shows the absorption fingerprints of exactly the kind of dense, embedding gas the model requires. Statistical stacking of X-ray data is consistent with heavy smothering rather than true silence. None of this is yet a verdict. Rival models remain live and are argued in the same journals. Perhaps some dots are supermassive primordial stars, single fusion-powered giants of up to 1 million solar masses, a stellar class permitted only in the universe's pristine first gas. Perhaps others are ordinary small black holes caught in rare, brief feeding frenzies beyond their theoretical speed limit. The population may prove to be a mixture. This is science mid-stride, and the honest label is being solved in real time, with the black hole star reading currently ahead on points. The population statistics deepen the strangeness in a way single objects cannot. Little red dots are not rare curiosities. At their peak era, they appear to be startlingly common, outnumbering the era's ordinary bright quasars many times over. If even a substantial fraction host massive black holes, then the young universe was carpeted with growing black holes at a density far beyond anything the standard census anticipated, an entire hidden generation of growth, wrapped in gas, invisible to every pre-Webb instrument because its light emerges reddened, compact, and X-ray smothered. And their disappearance is as informative as their abundance. By roughly 1.5 billion years after the Big Bang, the population collapses. The natural reading, the phase ends. The cocoons disperse or are consumed. The buried engines emerge as recognizable quasars. The dots do not die, they graduate. On that timeline, the bright quasar era that follows is the same population with its packaging removed, and the dots are the missing childhood photos of the objects astronomy has studied for 60 years. The spectroscopic detail that converted many skeptics is worth understanding because it is a lovely piece of physics. Several dots show a Balmer break, a spectral cliff produced by hydrogen-absorbing light, of a depth and sharpness that stellar populations struggle to reach, since a galaxy's stars span ages and smear the break. But hydrogen gas that is dense, warm, and enormously thick along the line of sight carves precisely such a cliff, while simultaneously broadening emission lines and muffling X-rays. One object's spectrum, the one nicknamed the cliff, is so extreme that analysts concluded no plausible arrangement of stars could reproduce it at all, while a black hole wearing a massive hydrogen atmosphere reproduces it naturally. In other words, the same single ingredient, an extraordinary envelope of dense gas, explains, in one stroke, nearly every anomaly on the charge sheet. Astronomy is rightly suspicious of one-ingredient miracles, but it is also trained to notice when the universe keeps handing back the same ingredient from independent directions. What would close the case is already scheduled. Deeper X-ray stacking will either find the smothered glow leaking through at the predicted whisper level or rule the cocoons airtight beyond plausibility. Long baseline monitoring will either catch slow variability, cocoon-filtered flickers on timescales of years, or certify a steadiness no accretion engine should manage. And spectroscopy across hundreds more dots will map the envelope properties as a population, testing whether they form the coherent family the black hole star model demands or dissolve into a mixed bag of imposters. Every one of those campaigns is underway now. It is entirely possible that by the time this video is a few years old, this item will have migrated from the unsolved catalogue to the solved one, and if so, it will be the happiest kind of obsolescence, because the solution would hand cosmology the origin story of its most important monsters. Here is why the outcome matters far beyond taxonomy. Remember the desert from the last part, the missing middle class of black holes, and the seed problem, the impossibility of growing billion-sun quasars from 100-sun corpses on the observed schedule. The little red dots sit at exactly the right cosmic era, in exactly the right numbers, at exactly the right implied masses, to be the answer, the seeds themselves, caught in the act of growing, infant supermassive black holes, swaddled in the gas they are devouring, passing through the desert inside cocoons that hid them from every previous telescope. If that reading survives, then the jars of this particular shelf connect, the jar labeled "Where are the middle black holes?" and the jar labeled "What are the little red dots?" would turn out to be the same jar, viewed from two sides. Every giant black hole in the modern universe, including the 4 million sun specimens sleeping at the center of your own galaxy tonight, would have spent its infancy as one of these small, patient, red lights. And notice the shape of the discovery itself, because you have seen it before tonight. An instrument built to hear one thing heard another. Arcade 2 rose over Texas to find the warmth of the first stars, and came back with the roar. The James Webb Space Telescope was launched to watch the first galaxies form, and the first thing it handed us was a new species of object nobody ordered. That pattern is not bad luck. It is the most reliable law in the history of instruments. Build a fundamentally better eye, and the universe will use it to change the subject. We have now been out among the signals, the stars, and the galaxies for 3 hours and more. For the 6th part of this catalogue, we come all the way home, to our own solar system, our own spacecraft, and our own front porch. You might expect the mysteries to shrink accordingly. They do not. They become, if anything, more unsettling, because these ones live where we live. Part 6. The Edge of Our Own System. On December 8, 1990, NASA's Galileo spacecraft came home for a visit. Bound eventually for Jupiter, it swung past Earth in a maneuver every deep space mission uses, the gravity assist, borrowing momentum from a planet to gain speed without burning fuel. Gravity assists are among the most precisely modeled events in engineering. Navigation teams account for general relativity, for the tides of the sun and moon, for the pressure of sunlight on the spacecraft's body, for the faint drag of the outer atmosphere. The predictions and the tracking agree, routinely, to fractions of a millimeter per second. That is the context you need for what happened next. When Galileo emerged from its flyby, radio tracking showed it moving 3.92 millimeters per second faster than every model said it should be moving. 4 millimeters per second, a slow walking pace of an ant, sounds like nothing. Against measurement precision of 1/10 of a millimeter per second, it is a 40 sigma scandal. Energy had appeared from nowhere, in the cleanest laboratory celestial mechanics possesses. And it was not a one-time bookkeeping slip. In January 1998, the near-Shoemaker spacecraft swung past Earth and came out 13.46 millimeters per second fast, the largest and cleanest case on record. Cassini's 1999 flyby showed a small effect. Rosetta's flyby in March 2005, 1.82 millimeters per second, unexplained, again. The near flyby deserves a closer look, because it is the case the whole file leans on. In January 1998, the spacecraft swept just 539 kilometers above Earth, a grazing pass, low over the planet, with the Deep Space Network's antennas locked on through approach and departure. The geometry was clean, the tracking nearly continuous, the atmospheric models at their best for such a low pass, and the books refused to balance by 13.46 millimeters per second, the largest discrepancy ever recorded. Translated into energy, the miss is almost insultingly small. For a spacecraft of NIR's mass, it amounts to roughly the energy of a dropped apple. That is the maddening scale of this anomaly. The universe appears to be slipping individual apples' worth of energy into billion-dollar trajectories, occasionally through a mechanism 35 years of professional scrutiny cannot name. A theft of millions would have been found by now. A theft of pennies, committed irregularly, is the hardest crime in bookkeeping to solve, and precision navigation is, at bottom, bookkeeping raised to a fine art. By the mid-2000s, this had a name, the Flyby Anomaly, and a growing case file at NASA's Jet Propulsion Laboratory, where the physicist John Anderson led the effort to systematize it. In 2008, Anderson's team published something tantalizing, an empirical formula. The size of each anomaly, they noticed, tracked the change in the spacecraft's declination, its angle relative to Earth's equator, between arrival and departure. A pattern tied to Earth's rotation axis smelled like real physics, perhaps some unmodeled interaction with the spinning planet, frame dragging miscounted, some rotational coupling nobody had written down. The formula fit every case on file. Science then did what science does. It tested the formula on the next flybys. Rosetta returned to Earth in 2007 and 2009 and showed no anomaly. Juno, in 2013, was watched deliberately, with instruments primed, no anomaly, by most analyses. The formula broke. The pattern dissolved. And that dissolution is the strangest part of the mystery, because an effect that appears in 1998 and 2005 then declines to appear in 2007, 9, and 13, fits neither an error nor a law of nature comfortably. Errors persist. Laws persist. This does neither. Understanding how such a tiny discrepancy can be certified at all requires a glance at the machinery, because the machinery is the reason the anomaly cannot be waved away. Deep space navigation runs on the Doppler effect. Stations of the deep space network beam a microwave tone to the spacecraft, which returns it faithfully. Motion along the line of sight shifts the returned frequency, and the shift reads out velocity with a precision of hundredths of a millimeter per second. Range measurements time the signal's round trip to meters. During an Earth flyby, tracking is nearly continuous. Geometry is superb, and the whole event lasts hours. A short, clean, exquisitely instrumented experiment in gravity. When the incoming and outgoing trajectory solutions refuse to join up without inserting an unexplained velocity jump, that refusal is documented across thousands of independent Doppler samples. The anomaly is not one reading. It is a seam that will not close in a garment sewn from thousands of stitches. The case has a human thread that deserves its line. John Anderson, who led much of this work at the Jet Propulsion Laboratory, spent a career as the keeper of exactly these unglamorous residuals. He also led the investigation of the Pioneer anomaly through its 2 decades. His teams did the least romantic work in space science, chasing millimeter-per-second discrepancies through thermal models, software conventions, and tide tables, publishing null results and retractions of their own hypotheses when the data demanded. That is what gives the surviving flyby residuals their weight. They are the leftovers after professional skeptics, with every incentive to close their own files, failed to. When such people publish an empirical formula and then publicly report that subsequent flybys broke it, you are watching science operate exactly as advertised, and the honest yield of all that discipline is the strangest possible sentence. Sometimes it happens, sometimes it does not, and no one knows why. The path forward is unusually cheap by space science standards, which makes the anomaly's persistence faintly maddening. Every future Earth gravity assist, and missions use them constantly, is a free experiment, requiring only that tracking be scheduled and analyzed with care. The European JUICE mission's Earth passes, and every future flyby by missions bound for the outer planets will each get modern scrutiny. Some researchers have proposed dedicated smallsat missions, cheap spacecraft flown through the anomaly's claimed geometry repeatedly, with laser ranging and drag-free sensors, to force the effect into repeatability or extinction. Until someone flies that experiment or an ordinary flyby misbehaves under full modern instrumentation, the file sits where it has sat since 1990, a few millimeters per second of unexplained energy, appearing intermittently in the most carefully measured trajectories our species produces. Every conventional suspect has been interrogated at length. Atmospheric drag, wrong size, wrong sign. Ocean and solid body tides, modeled, insufficient. Relativistic frame dragging, calculated, thousands of times too small. Magnetic coupling, thermal radiation from the spacecraft, software sign conventions, the subtleties of converting Doppler data between reference frames. Each has been proposed. Several have partisans. None survives all the cases. Exotic proposals, a thin ring of dark matter girdling Earth's orbit, modifications to inertia at low accelerations, can be tuned to fit the positives and then stand embarrassed before the nulls. And the community carries a scar that keeps it humble in both directions, the Pioneer anomaly. For 2 decades, both Pioneer spacecraft showed an unexplained sunward deceleration that spawned hundreds of new physics papers, until 2012, when meticulous thermal modeling showed the cause was heat, the spacecraft's own generators, radiating unevenly, pushing back like the faintest imaginable rocket. Mystery dissolved, physics intact, lesson learned. The Flyby Anomaly has now received the same class of scrutiny for longer and has not dissolved. So the honest label is unresolved and capricious. It is either a subtle, intermittent modeling error that 3 decades of navigation experts have failed to locate, which would itself be remarkable, or it is the cheapest doorway to new physics ever offered, sitting in archived tracking data, priced at a few millimeters per second. The European Space Agency's JUICE mission and future Earth flybys will each get the full instrumentation treatment. Every pass is another roll of the dice. Until one comes up anomalous under modern scrutiny, the file stays open, and every spacecraft that borrows speed from our planet does so under a small, unresolved question mark. Our machines misbehave near Earth by millimeters. Farther out, it is the solar system itself that misbehaves, by simply stopping. Beyond Neptune, the solar system keeps a second asteroid belt, grander and colder than the first. The Kuiper belt is a broad donut of icy bodies. Pluto is merely its most famous citizen, holding, by current estimates, hundreds of thousands of objects larger than 100 kilometers and countless smaller ones, the preserved rubble of the solar system's construction. Theory has clear expectations for such a structure. The disk of gas and dust that built the planets should have thinned gradually with distance, and its leftover debris should do the same, a long, slow taper, dwindling for hundreds of astronomical units. An astronomical unit is the distance from the Earth to the Sun. Neptune orbits at 30 of them. The Kuiper belt does not taper. At roughly 48 to 50 astronomical units, the population of its classical, well-behaved objects collapses, abruptly, like terrain dropping off a sea cliff. Astronomers call it exactly that, the Kuiper Cliff. Beyond the line, where models predict a countryside of icy bodies, surveys found near emptiness. And this is not a matter of failing to look. Distant objects are fainter, and that bias was the first suspect, but decades of deepening surveys have retired it as the full answer. If the belt continued smoothly past 50 astronomical units, modern searches would have harvested a crowd of objects out there. The crowd is missing. The solar system's construction site appears to end at a fence, and nothing in standard planet formation builds fences. The belt's own discovery story is worth a moment, because it frames how young our knowledge of this frontier really is. The idea of a trans-Neptunian debris disk was proposed in the mid-20th century. The Irish astronomer Kenneth Edgeworth sketched it in the 1940s, and Gerard Kuiper discussed the region in 1951. But for decades it remained pure conjecture, with Pluto as its lone, anomalous resident. Then, in the late 1980s, David Jewett and Jane Liu began a search that colleagues considered quixotic, pointing telescopes at empty ecliptic sky, night after night, hunting for anything slow and faint that moved. The search consumed 5 years. In August 1992, from Mauna Kea, they found it, a dim, reddish point creeping along at 44 astronomical units, the first Kuiper belt object after Pluto itself. In the 3 decades since, the census has grown past 3,000 known objects, and an entire third zone of the solar system, as real as the rocky planet's realm or the gas giants, has materialized in the catalogues within a single working career. The cliff at its edge is, in that light, a brand new mystery about a brand new country. We discovered the territory, mapped its heartland, and ran into its inexplicable border, all within 30-odd years. That youth explains why the field holds its conclusions loosely, and why the cliff could still transform under better data. Survey coverage of the outer belt remains genuinely thin, beyond 50 astronomical units. An object the size of a large city reflects less sunlight than a candle seen from across a continent, and it moves so slowly that telescopes must re-image the same field across months to certify the motion. The surveys that established the cliff were rigorous but narrow, strips of sky, statistically extrapolated. It remains possible that the outer zone holds substantial mass in forms current searches penalize, objects on tilted orbits that spend their time far from the ecliptic plane, dark surfaces, or a population clustered in the distant reaches the Subaru work is only now sampling. Every one of those escape hatches is testable, and the testing is funded and scheduled. What is not really in doubt is the central strangeness. Whichever way the census resolves, the smooth, gradually fading disk that theory once promised is not what is out there. Our solar system ends, or pauses, in structure, and structure is always a fossil of events. The candidate explanations reach back to the solar system's birth. Perhaps the disk was born truncated, the sun formed in a crowded stellar nursery, and a passing sibling star, sweeping close in those first few million years, could have sheared off the disk's outer edge, or the fierce ultraviolet light of a nearby giant star could have boiled it away. Perhaps the belt formed farther in and was rearranged. Neptune, migrating outward in the early chaos, herded and scattered the icy population, and some models can park an edge near 50 astronomical units. And there is a third idea, older than today's headlines, that refuses to die. Perhaps something massive, an unseen planetary body, long ago swept the zone beyond the cliff clean, shepherding its edge the way moons shepherd planetary rings. The cliff shepherd is an older, humbler suspect. Neither has been found. The searches continue. The cliff abides. And in just the last 2 years, the mystery has grown a genuinely wonderful complication. NASA's New Horizons spacecraft, the probe that flew past Pluto in 2015, is still alive, still outbound, and still doing science. Ride with it for a moment. 14 kilometers of new distance every second, the sun astern reduced to a brilliant, heatless star, radio commands taking half a day to arrive. Aboard, among the instruments, rides a small dust counter, designed and built by university students, a plate that registers the tap of each microscopic grain that strikes it. Out past 50 astronomical units, where the maps say the belt has ended, and the dust should be thinning toward interstellar cleanliness, the counter has kept ticking. Steady, patient, punctual taps, more dust than an ending belt should shed, arriving out of territory the catalogue calls empty. Small contradictions, delivered 1 grain at a time, to a listening post 4 hours away by radio. The instrument doing that listening carries a story worth telling in full. The dust counter aboard New Horizons is named the Venetia Burney Student Dust Counter, the first science instrument on any planetary mission designed, built and operated by students. And its namesake is the 11-year-old English schoolgirl who in 1930, over breakfast, proposed the name Pluto for the newly discovered planet. Venetia Burney lived to see the spacecraft launch toward the world she named, with an instrument bearing her own name bolted to its hull. That instrument has now become the only dust detector ever to operate at such distances, and its humble tally, impacts per year, at each increment of distance, has quietly contradicted the tidy picture of a belt that ends. Grain by grain, the student's plate is reporting that the solar system's attic is dustier, farther out, than the blueprints say it should be. The stakes for planet formation theory are larger than the word dust suggests. The Kuiper Belt's cold classical population, the dynamically calm objects on nearly circular orbits, is believed to be the most primordial material accessible to observation, bodies that formed in place and were never scattered, unmodified leftovers of the original disk. New Horizons flew past one of them, the lobed pristine world Arakoth, and read in its gentle contact binary shape the signature of quiet assembly, particles settling together softly rather than colliding violently. If that serene construction zone extends, or resumes, beyond the supposed cliff, then the Sun's disk was substantially larger than the textbook version, and its outer architecture, edges, gaps, second belts, records events we have not identified: a stellar flyby, an unseen shepherd, a resonance ghost of Neptune's ancient wanderings. Around other stars, our telescopes routinely image debris disks with exactly such multi-ring architecture. The question the dust is raising is whether our own home system, seen from outside, would look just as ringed and gapped, and if so, what carved ours? The next decade should answer it. The Vera Rubin Observatory's All-Sky Survey is projected to multiply the known trans-Neptunian population several-fold, mapping the cliff's far side with statistics no earlier survey approached, while New Horizons, healthy, fueled and funded into the 2030s, continues outbound through the very territory in dispute, its student instrument still counting. There is a fair chance the spacecraft will pass directly through whatever the Subaru candidates trace, taking the census from inside as Rubin takes it from outside. Rarely does a mystery about the deep outer solar system come with two independent verdicts already scheduled and paid for. The cliff, the gap, or the second belt, one of those maps will be drawn correctly within years, and our solar system will get, at last, an honest property line. Dust is made by collisions among larger bodies, so persistent dust implies a persistent population. And in the same window of years, deep surveys with the Subaru telescope, searching the space ahead of New Horizons, have reported candidate objects clustered at 70 to 90 astronomical units, with a comparatively empty lane between them and the classical belt. Follow the implication carefully, because it would redraw the map. The Kuiper Cliff might not be an ending at all. It might be a gap, a divide between our known belt and a second, farther population waiting in the dark. Other planetary systems imaged from outside often show rings with gaps between them. Ours may as well, and gaps in planetary systems are usually carved by something. So the status of our own backyard's edge, honestly stated, is this: we do not know whether the solar system's disk ends at 50 astronomical units, pauses there, or was fenced there, and the answer is being changed in real time by a spacecraft with a student-built instrument and a telescope on a Hawaiian mountain. We have mapped the shorelines of worlds around other stars. Our own shoreline remains unsurveyed. There is something almost domestic about that, like discovering that the property line of your own home was drawn in pencil and may extend past the hedge. Past the cliff, past the farthest belts, lies the true boundary of the sun's dominion, the wall where our star's breath finally fails against the interstellar wind. That wall exists. We have imaged it, and the first image came back bearing a mark that no one predicted and no one has explained. The sun does not merely shine, it exhales. A wind of charged particles, 1,000,000 tons of it every second, streams from the sun in all directions at hundreds of kilometers per second, inflating a bubble in the interstellar medium. The bubble is called the heliosphere, and everything you have ever known or touched resides inside it. Every planet, every human artifact save 5 outbound spacecraft, every night sky ever observed by anyone. Its wall, where solar breath and interstellar gas reach equilibrium, lies roughly 100 astronomical units out. That wall cannot be photographed in ordinary light. It is too dilute, too dark. But nature allows a trick. Where the boundary regions seethe, collisions between charged and neutral particles occasionally mint energetic neutral atoms, fast particles without electric charge, which ignore every magnetic field and fly in straight lines. Catch them, note their arrival directions, and you can build an image of the unphotographable, a map of the bubble's wall, drawn in atoms instead of light. The bubble itself was once a heresy, and the memory is instructive. In 1958, a young physicist named Eugene Parker calculated that the sun's outer atmosphere could not sit still. It must expand, continuously, as a supersonic wind filling the solar system. The idea was received poorly. Referees recommended rejecting the paper, and one eminent colleague suggested Parker read up on the subject before publishing again. 4 years later, the Mariner 2 spacecraft, cruising to Venus, flew through the wind and measured it streaming past exactly as predicted, and the heliosphere, the wind's great bubble, entered the textbooks. Parker lived to see a spacecraft named for him fly into the Sun's atmosphere itself, the first NASA mission ever named for a living scientist. The ribbon is the latest chapter of the same story arc. Each generation maps one layer of the Sun's dominion and finds the next layer stranger than predicted. The wind was a heresy, then a fact. The bubble's wall was a diagram, then a photograph. The photograph came back wearing a stripe no one ordered, and somewhere in the next generation's data, presumably, waits the stripe's own successor. That was the mission of IBEX, the Interstellar Boundary Explorer, a small, inexpensive NASA spacecraft launched in October 2008 into a high Earth orbit, spinning patiently, counting atoms. In 2009, the team assembled the first complete all-sky map of the heliosphere's boundary, expecting the gentle, structureless gradients that every model predicted. What the map showed instead became one of the great instrument surprises of the era. Slashing across the entire sky, through the constellations of the northern reaches, ran a bright, narrow arc, a band of energetic neutral atom emission 2 to 3 times more intense than everything around it, about 20 degrees wide, sweeping most of the way around the celestial sphere. The team called it, plainly, the ribbon. David McComas, the mission's principal investigator, was blunt in the way scientists reserve for genuine shocks. No model had predicted it. The mission's theorists, shown the map, had not believed it. Our home bubble, photographed for the first time, had a stripe painted on it. 15 years of work have yielded one solid clue and one leading suspect. The clue, the ribbon, is not random. It traces, with remarkable fidelity, the locus of directions where the local interstellar magnetic field, the galaxy's own field, draped around our bubble like current around a stone, runs perpendicular to the line of sight. The galaxy's magnetism, in other words, is somehow organizing the glow. The leading mechanism, called secondary energetic neutral atoms, is a boomerang built from coincidences. Solar wind ions escape the bubble as neutral atoms. Outside, some are re-ionized and trapped, gyrating around the interstellar field lines. A fraction are re-neutralized while aimed, by chance, precisely back at the inner solar system, returning years after they left, from the directions where the field's geometry permits the return flight. It is an elegant story. It explains the geometry and much of the ribbon's slow evolution across a solar cycle. It is also one of roughly a dozen mechanisms proposed within a few years of the discovery, and the community has never been able to close the case. The details of energy, width, and time variation keep every hearing contentious. The ribbon has also been caught changing, and its changes are evidence of the most useful kind. Across the years of IBEX's watch, the ribbon dimmed, shifted, and rebounded in loose synchrony with the solar wind's own cycles. When the sun's output waned, the ribbon's glow followed, after a delay of a few years. That delay is a measuring stick. It is roughly the round-trip time the secondary atom boomerang requires. Solar wind out, neutralization, capture, return. A painted-on feature of the interstellar medium would not care about our star's moods. A structure manufactured from recycled solar wind must echo them on exactly this lag. The correlation is among the strongest arguments the leading model owns. Yet even here the fit is imperfect. The response's details differ across energies in ways the simple picture does not predict, and so the ribbon's own weather, like everything else about it, currently testifies for the defense and the prosecution at once. It helps to place the ribbon beside the only ground truth we possess. 2 spacecraft have physically crossed the boundary the ribbon decorates: Voyager 1 in 2012, Voyager 2 in 2018, each reporting the moment the solar wind died around it and interstellar plasma closed in. Those crossings were epochal, but they are two needle pricks through a surface billions of kilometers across. 2-point measurements of a structure ibex images globally. The two kinds of knowledge need each other. The Voyagers found the boundaries' local thickness, fields, and turbulence. The atom maps supply the shape of everything the Voyagers will never live to reach. It is precisely in combining them that the current picture keeps failing. Models tuned to match the Voyager crossings misdraw the ribbon. Models tuned to the ribbon misplace details the Voyagers measured directly. Our home bubble is, at present, a house that does not match its own floor plan. IMAP's advantage in settling this is not merely sensitivity, but time resolution. New global maps every few months instead of every year, sharp enough to watch the ribbon's weather as it happens, rather than reconstructing it afterward. If the boomerang model is right, the coming solar cycle will play across the ribbon like a slow signature, energy band by energy band, on schedules the model must predict in advance. Prediction in advance is the standard this mystery has never yet met. Within a few years, the ribbon will either start honoring forecasts, becoming the first weather system of interstellar space to be understood before it happens, or it will break the forecasts and force the field to concede that the mark on our bubble's wall is stranger than any of the dozen stories told about it. Either outcome will be the best data this question has ever had. The referee has just taken the field. In September 2025, NASA launched IMAP, the Interstellar Mapping and Acceleration Probe, to a station at the L1 point between Earth and Sun. Its atom-counting instruments carry roughly 15 to 35 times the collecting power of ibexes, mapping the boundary sharply every few months. Within a few years, IMAP should either watch the ribbon behave exactly as the boomerang model demands or catch it doing something none of the models can survive. The same maps should settle a companion argument about the bubble's overall shape, whether our heliosphere trails a long comet tail or is shaped, as one persistent school holds, like a croissant. It says something about this field that the shape of our own home in the galaxy is still an open multiple-choice question. Until those maps arrive, the standing summary is this. One star's breath holds back the galaxy, and everything you love lives inside the bubble it blows. The first true picture of that bubble's wall came back with a mark on it, and after 15 years, we are still arguing about the paint. And with that, the objects are behind us. Signals, stars, black holes, galaxies, spacecraft, walls, every mystery so far has lived somewhere. For the seventh and final part of this catalogue, we go after the mysteries that live everywhere, the ones written into the arithmetic of the universe itself. These are the anomalies that do not sit in any telescope's field of view, because every telescope is inside them. Part 7. A universe that will not add up. In its first 3 minutes, the universe ran a chemistry experiment, and we possess the lab report. The theory is called Big Bang nucleosynthesis, and it is one of the proudest calculations in all of physics. Take the universe at 1 second old, a fireball of protons, neutrons, and radiation at 10 billion degrees, and let it expand and cool according to known nuclear physics. The calculation predicts, from first principles, exactly what the fireball should have forged before it became too cold and thin to continue: hydrogen, about 3/4 of everything by mass; helium-4, about 1/4, a trace of deuterium, heavy hydrogen, a few atoms in every 100,000, and a whisper of lithium-7, roughly 1 atom for every 2 billion hydrogens. 4 predictions. No free parameters worth mentioning once the ordinary matter density is fixed by observations of the infant universe's light. 3 of the 4 predictions are triumphs. The helium fraction, measured across the universe, matches. Deuterium, so fragile that stars only destroy it, making its primordial abundance readable in pristine distant gas clouds, matches the prediction with a precision that still astonishes the people who compute it. Hydrogen matches. And lithium, the third element of the periodic table, the one in the battery of the device you are listening to, fails. The oldest stars of our galaxy carry about 1/3 of the lithium the Big Bang should have given them. The theory that gets 3 elements gloriously right gets the 4th wrong by a factor of 3, and it has now been wrong, without interruption or explanation, for more than 40 years. The measurement itself is a beautiful piece of astronomy. In 1982, the French astronomers François and Monique Spite, a husband and wife team, measured lithium in the atmospheres of the galaxy's most ancient stars, the metal-poor survivors of the halo, formed from nearly unpolluted primordial gas. They found something unexpected and lovely. Across a wide range of temperatures and compositions, these old stars carry almost exactly the same lithium abundance, a flat, uniform value, since named the Spite Plateau. A plateau is precisely what a primordial abundance should look like. Everyone inherits the same starting allowance. The trouble is the altitude. The plateau sits at 1/3 of the predicted value, and it is too flat to explain away easily. 3 escape routes exist, and all 3 are blocked. Route 1. The stars ate the evidence. Lithium is fragile, burning at temperatures stellar interiors easily reach, so perhaps ancient stars have slowly destroyed their allowance. The objection is the plateau's crispness. Destruction depends on a star's mass, temperature and rotation, and should vary star by star, smearing the plateau into a scatter. The plateau is not smeared. Uniform destruction across billions of different stars, all conspiring to the same final value, strains belief, though refined versions of this idea remain the field's least exotic hope. Route 2. The nuclear physics is wrong. Perhaps some reaction rate in the primordial network was mismeasured. This has been checked to exhaustion, including by the Lunar Collaboration, which rebuilt the key reactions in a laboratory under a mile of Italian rock beneath the Gran Sasso Massif, where cosmic ray noise cannot reach. The rates held. The discrepancy held. Route 3. New physics. A decaying exotic particle in the first minutes. A drifting fundamental constant. A sterile neutrino, tilting the neutron budget. Each can be tuned to fix lithium. And nearly every tuning that fixes lithium damages the exquisite deuterium agreement, like a mechanic who repairs the brakes by disconnecting the steering. The measurement chain behind the problem is a masterpiece of stellar archaeology, and its solidity is why the anomaly cannot be shrugged off. Reading lithium in a star means reading one faint absorption line in its spectrum and converting that line's depth into an abundance, a conversion that requires modeling the star's atmosphere, its temperature layer by layer, its convection, its departures from equilibrium. 4 decades of refinement have hardened every link. The stars in question are the galaxy's living fossils, some with less than 1,000th of the sun's metal content, dredged from the halo by survey after survey. Their temperatures are pinned by multiple independent methods. The lithium line's atomic physics is laboratory grade. And the plateau has been reconfirmed in ever larger samples, extending even to stars in other galaxies' shredded remnants, now drifting through our halo. Wherever ancient, unpolluted stars are found, they carry the same discipline shortage, 1/3 of the predicted allowance, everywhere, as if the universe issued the deficit uniformly. Meanwhile, the other side of the ledger hardened as well. The prediction's inputs, the density of ordinary matter, the behavior of neutrons in the first minutes, were once adjustable enough to hope lithium might bend. The satellite era removed the slack. The Planck mission read the ordinary matter density from the microwave background to fractions of a percent, and with it, Big Bang nucleosynthesis became a parameter-free machine. Feed in that density, and the theory now predicts deuterium so precisely that observers race to match its error bars, and they do match, exquisitely. The same crank of the same machine outputs the lithium value, 3 times too high. That is what elevates a discrepancy into a problem. The successful predictions and the failed one are not separable. They emerge from one calculation, one universe, one set of physical constants. You cannot repair lithium without explaining why deuterium, its sibling from the same 3 minutes, needed no repair at all. One further twist keeps the field honest about blaming the stars. Lithium in the universe at large has risen since the beginning. Cosmic rays and certain stars manufacture it. So young objects like meteorites and the present-day interstellar gas carry several times the primordial value. The ancient stars sit below the primordial prediction, while everything younger sits above it, and any stellar destruction mechanism must therefore erase lithium in exactly the old stars, by exactly the uniform factor, while sparing the general inventory's growth. Models invoking slow internal mixing and diffusion over 10 billion years can be built to do this, and they remain the establishment's least uncomfortable refuge. But they must be tuned with a delicacy that many in the field find as suspicious as new physics would be. Between a conspiracy of stars and a crack in the first 3 minutes, the community keeps both files open, and the recipe's one wrong line keeps its place in every review of what remains unexplained. It is worth stepping back to see why so small a discrepancy commands such loyalty from the people who study it. The first 3 minutes of the universe are the earliest era for which physics can make hard, checkable predictions. Everything before that is inference. Everything after has messy astrophysics layered on top. Big Bang nucleosynthesis is therefore the deepest direct handshake between observation and the beginning of time, and it has exactly 4 fingers: hydrogen, helium, deuterium, lithium. 3 fingers grip perfectly. To shrug at the 4th is to shrug at a flaw in our clearest window onto the universe's first moments, and the history of physics is pointed on this subject. The perihelion of Mercury drifted from Newton's prediction by an amount so small it took decades to certify, and the resolution was general relativity. Small, clean, persistent discrepancies in otherwise triumphant theories are precisely where physics has repeatedly kept its revolutions. Lithium may well die a mundane death in the convective layers of old stars, but it has earned the respect of being watched closely by people who remember Mercury. The problem also once had a sibling, and the sibling's fate shows the field's willingness to let mysteries die when the evidence demands it. In the 2000s, several groups reported traces of lithium-6, a more fragile isotope that the Big Bang should have produced in only vanishing amounts, in the same ancient stars, at levels thousands of times above prediction. For a few years, astronomy carried 2 lithium problems, and theorists built exotic machinery to feed both. Then better spectral modeling, accounting honestly for the churning convective motions of stellar surfaces, showed the lithium-6 signal was a mirage, an artifact of asymmetric line shapes mimicking the isotope's fingerprint. The second lithium problem was closed, formally and without regret. The first one survived the same improved scrutiny untouched. That contrast is the quiet certification of a real anomaly. The community that cheerfully executed one lithium problem when the data turned has kept the other on the books for 40 years, because the data never turned. So the lithium problem sits in the reviews, year after year, carrying the same one-line status, the sole surviving inconsistency of Big Bang nucleosynthesis. It is small, as anomalies go. 1 element, 1 factor of 3. But it is written into the universe's opening chapter, and it will not close. Perhaps some quiet stellar astrophysics will one day dissolve it. Perhaps it is the first legible typo in the standard model of cosmology, small enough to ignore, persistent enough to be a message. An honest catalogue keeps it on the shelf, label facing out. One number from the first 3 minutes refuses to balance. The next mystery may also date from the first second, and it hides in the emptiest places that exist. Between the galaxies, the universe keeps its true wilderness. The cosmic web, the foam-like architecture of all matter, consists of bright filaments and walls of galaxies wrapped around enormous dark cells called voids, cavities hundreds of millions of light-years across, where matter thins to almost nothing. A void is the least eventful place reality offers. No stars form there. No winds blow. By every classical expectation, a void should also be magnetically dead, because magnetic fields, as far as astrophysics understands them, are made and maintained by matter in motion, churning stellar interiors, spinning galactic disks, turbulent plasmas. Galactic magnetic fields are understood this way, as dynamos, seeded weak, amplified by rotation over billions of years. No matter, no motion, no dynamo, no field. The voids should be clean. They appear not to be. The evidence is indirect, ingenious, and maddening. Blazars, galaxies whose central black holes fire jets almost directly at Earth, send beams of extremely energetic gamma rays across the voids. Physics dictates what should happen en route. The highest energy photons collide with the faint ambient light that fills space and shatter into pairs of electrons and positrons. Those pairs then strike the microwave background and re-radiate slightly gentler gamma rays. The upshot is a prediction. Around every distant blazar, telescopes should see a halo of secondary gamma rays. The cascades glow, arriving alongside the direct beam. In 2010, researchers analyzing data from the Fermi telescope reported the halos are missing. Systematically. The cascades launch, that part is required physics, but their glow does not arrive. The tidy explanation is a magnetic field where no field should be. Even an almost inconceivably weak field threading the voids, a tenth of a femtogauss, some 10 million billion times weaker than the field that swings a compass needle, would deflect the cascading electron-positron pairs, smearing their re-radiated glow so broadly across the sky that no telescope would register it. The missing halos, read this way, are a detection. The voids are magnetized, faintly but everywhere, coherently, across megaparsecs. And that conclusion, mild as it sounds, has no comfortable origin story. Galactic pollution, fields blown out of galaxies by winds, struggles to reach the deep voids at the required coherence. Which leaves the primordial option, that these fields were forged before the galaxies, before the stars, before atoms, in the universe's first second, during inflation or a phase transition, and have survived ever since as fossils, diluted but unbroken, preserved in the one environment nothing ever disturbed. If so, the voids are the universe's archive vault, and every magnetic field you have ever used, the Earth's, a compass's, the magnet on your refrigerator, descends, by amplification, from a relic older than matter itself. The theoretical stakes of the primordial option deserve unpacking, because they connect this whisper to the most fundamental unsolved structures in physics. Making magnetic fields in the early universe turns out to be embarrassingly difficult. The equations of electromagnetism in an expanding cosmos conspire, through a property called conformal invariance, to dilute any field away almost as fast as it is made. Inflation-era magnetogenesis therefore requires that symmetry to fail, new couplings, new fields, physics beyond the standard model by construction. The alternative venue is a cosmic phase transition, when the infant universe's fields snapped from one vacuum state to another. The churning of that transition could have wound up magnetic fields like eddies behind a waterfall. Either way, a confirmed primordial field would be a message from an epoch no telescope can image, a fossil not of matter, but of the vacuum's own history. Cosmologists have even proposed reading its helicity, whether the field's tangles prefer left-handedness or right, as a record of the same broken symmetry that left the universe with more matter than antimatter. A faint field in empty space could, in the most optimistic reading, be a signed confession from the first second. Independent lines of evidence have begun to brush against the same conclusion from other directions. Surveys of the cosmic web's filaments, the bridges of gas between galaxy clusters, have detected polarized radio glows implying magnetism threading even those tenuous spans, at strengths dynamos struggle to reach so far from galaxies. Statistical studies stacking millions of galaxy pair sightlines report rotation measure signals consistent with magnetized bridges. None of these reach into the true void interiors, where only the blazar cascade method probes, but they tighten the frame. Magnetism appears more widespread, at larger scales and earlier times, than the pollution model comfortably supplies. The picture assembling itself, cautiously, is of a universe that was never magnetically clean, born with a whisper of field everywhere, which galaxies later amplified into the loud fields we measure nearby. The decisive instruments are pleasingly concrete. The Cherenkov telescope array, over 100 dishes rising on sites in the Canary Islands and Chile, will be able to detect the pair halos directly if the fields sit near the current lower bounds, converting an absence into an image, literal photographs of the smeared glow, its size and shape encoding the field's strength and structure. On the radio side, the square-kilometer array will chart rotation measures across millions of sightlines, mapping cosmic magnetism's geography at a scale that will either find the void's edges going quiet, pollution's signature, or humming faintly everywhere, the primordial signature. For a mystery whose subject is nothing, arranged in the largest empty rooms in existence, the resolution will come from some of the most substantial machines humanity has ever pointed at the sky. There is a fitting symmetry in that. To feel the scale of the claim, it helps to walk into a void properly. Choose a direction between the great galaxy chains and travel. Within a few million light-years you leave the last dwarf galaxies behind, and then there is simply nothing. No stars, no gas worth naming, a darkness so complete that if you stood in a void's heart, the entire sky would offer not one naked-eye star, only the faint smudges of distant galaxy walls. Cross it at the speed of light, and the crossing consumes 100 million years or more. Now recall what the blazar measurements imply, threading that entire emptiness, everywhere, a magnetic field, absurdly weak, 1,000,000 billion times fainter than Earth's, but present, ordered over spans of millions of light-years, occupying rooms that have never once hosted the machinery that makes fields anywhere else. It is like finding the faint smell of smoke in a sealed vault that has never contained fire. The smell is nearly nothing. The problem is that it should be exactly nothing. The amplification chain that would connect such a seed to every magnet on Earth is one of astrophysics' great untold production stories. Take a primordial whisper of field, the void's preserved sample, and fold it into a collapsing proto-galaxy. Compression alone strengthens it 1,000,000-fold. Let the young galaxy rotate, and the dynamo begins, differential rotation stretching field lines, turbulence folding them, each cycle roughly doubling the strength, until, over a few billion years, the whisper has been amplified to the microgas fields that thread the Milky Way today, which in turn spawned the field frozen into the collapsing cloud that became the Sun, which stirred the dynamo now running in Earth's molten iron core, which swings every compass and shields every living thing from the solar wind. If the primordial reading is right, that unbroken chain of inheritance runs from the universe's first second to the magnet holding a child's drawing to a refrigerator door. The voids matter because they are the only link in the chain still preserved in its original condition, the family archive, unedited, kept in the emptiest attic in existence. The honest complications, Some plasma physicists argue instabilities could drain the cascade's energy en route, mimicking the missing halos without any field. A recent proposal suggests galactic fields might seep outward over cosmic time more effectively than believed. The lower bounds on the field have survived reanalysis so far. The next-generation Cherenkov telescope array, coming online in the late 2020s, should finally either image the halos and measure the fields, or force the alternatives to the front. Until then, the emptiest places in existence hold a property nothing available could have given them: a whisper of order in the perfect dark, possibly the oldest artifact in the universe. And so we arrive at the final mystery. It concerns no object, no signal, no place. It concerns the whole, and us. Because the last open question in this catalogue is whether we know, at the most basic level, how we are moving through the universe. Modern cosmology rests on a single founding assumption, stated in every textbook's first chapter. It is called the cosmological principle. At sufficiently large scales, the universe is the same everywhere, and the same in every direction. No special places, no preferred directions, no center, no edge. Every measurement of dark energy, every model of cosmic history, every value of the universe's age and fate is computed on top of that assumption, the way every floor of a building stands on its foundation. The final mystery of this catalogue is a crack being measured, right now, in that foundation. Begin with what is solid. The cosmic microwave background, the Big Bang's afterglow, arriving from every direction, is not perfectly uniform in temperature. Its largest feature is a dipole. One half of the sky is very slightly warmer, the opposite half very slightly cooler, by about 0.1%. The universal interpretation is motion. We are not at rest. The Sun, carried by the spinning galaxy, which is itself falling through its neighborhood, moves at about 370 kilometers per second relative to the background, and that motion Doppler warms the sky ahead of us and cools the sky behind. 370 kilometers per second, you have crossed about 10,000 kilometers of universe since this item began. That number is the bedrock. It defines the universe's rest frame, the still water against which all cosmic motion is measured. In 1984, two cosmologists, George Ellis and John Baldwin, pointed out that the bedrock could be tested. If the microwave dipole is truly caused by our motion, that same motion must leave a second, independent fingerprint. Move through a rain of light sources, and the sources ahead of you appear very slightly brightened and crowded together, relativistic effects, small but exactly calculable. Count enough faraway objects evenly across the sky, and you must find a matching dipole in the counts, slightly more sources ahead of us than behind, in precisely the direction we travel, at precisely the amplitude our speed dictates. It is a pure consistency check, the kind of test a sound theory passes without noticing. For 4 decades, the catalogues were too small to run it. Now they are large enough, and the test is failing. Radio astronomers ran it first, counting hundreds of thousands of radio galaxies. From 2011 onward, analysis after analysis found the count's dipole pointing in approximately the right direction, but too large by a factor of 2 to 4. Radio surveys have quirks, so the decisive move came in 2021, when a team led by Nathan Seacrest ran the test on an entirely different instrument's harvest, 1.36 million quasars, catalogued in the infrared by the WISE Space Telescope. Different wavelength, different hardware, different systematics, different objects. The result? A dipole aligned with the microwave backgrounds and roughly twice as large as our measured motion can produce. The statistical strength of that single result was 4.9 sigma, about 1 chance in 2 million of arising from noise. Combine the radio and quasar results, and the tension now stands beyond 5 sigma, the threshold physics traditionally calls a discovery. Some 2025 compilations place it near 6. And a 2025 analysis of over 1 million quasars with measured redshifts pushed the knife deeper, implying an effective motion of some 1,700 kilometers per second, 4 to 5 times the bedrock value, along the same axis. The light of the universe and the matter of the universe ask the same simple question: how fast are we moving? Are returning different answers. Watch what this looks like on the sky itself, because the image is worth holding. Strip away the stars in your mind, strip away the Milky Way's band, leave only the quasars, 1.36 million pinpricks, each a feeding black hole billions of light years out, scattered across the whole celestial sphere. Now count them, hemisphere against hemisphere, ahead of our motion and behind it. The excess ahead is tiny, a fraction of a percent, utterly invisible to any eye, but it is there, in the statistics, steady and directional, a few thousand more lights ahead of us than behind us, beyond what our motion should produce. The entire sky, tilted, like a floor level to every sense, on which a dropped marble nonetheless rolls, always, toward the same wall. The history of how we learned our own motion gives the current crisis its proper irony. The microwave dipole was hunted through the 1960s and 70s with heroic improvisation, detectors on mountaintops, on balloons, and most famously aboard a U-2 spy plane, flown in long, cold arcs over California by physicists who had borrowed Cold War hardware to ask a cosmological question. When the dipole resolved, it delivered one of the 20th century's quiet humiliations. Not only does the Earth move, and the Sun, but the entire galaxy is falling, hundreds of kilometers per second, toward a distant concentration of mass. Textbooks absorbed it smoothly, as textbooks do. But notice what was actually conceded. Our standard of cosmic rest was rebuilt, from scratch, on the interpretation of one pattern in one radiation field. The Ellis and Baldwin test was proposed almost immediately as the way to check that single load-bearing interpretation. It waited 40 years for catalogues deep enough. The first full-strength check of the foundation, in other words, is happening now, and it is the check that is misbehaving. It is worth dwelling on how conservative the failing test really is, because its modesty is its menace. The Count's test does not ask what quasars are, how they evolve, or how bright they should be, questions with room for error. It asks only, are there equal numbers, per patch of sky, fore and aft, once our measured motion is accounted for? Isotropy, plus known velocity, fixes the answer by pure geometry. Nearly every systematic error anyone has proposed, dust near the galactic plane, catalogue masking, survey depth varying across the sky, has a signature that analysts can hunt for directly, and the anomaly's defenders have spent years hunting, cutting the sky into hemispheres, excising the galactic plane entirely, re-deriving the result in independent subcatalogues. The dipole excess, in their accounting, survives every amputation, pointing steadily along the axis of our motion, as if the universe were annotating the microwave background's number with a polite red correction mark. The critics' counter-audits, applying different cuts, watch the significance soften. Both camps use the same public data. The disagreement is now about statistical craft, which is exactly where a foundational question should be fought, and exactly where laypeople least expect cosmic drama to live. It is fair to ask what actually changes if the anomaly is confirmed, and the honest answer is, the corrections would reach into nearly everything, mostly invisibly. Cosmology uses our measured motion constantly, as silent plumbing. Every supernova's redshift is adjusted for it before entering the datasets that reveal dark energy. Every map of cosmic structure subtracts it. Every claimed bulk flow of galaxies is measured against the frame it defines. If our true velocity differs from the textbook number, or if the frame itself is subtly tilted, Those corrections have been misset across decades of precision results, not catastrophically, but pervasively, in the manner of a survey whose benchmark elevation was carved a few centimeters wrong. Some tensions elsewhere in cosmology might ease, others might sharpen. Every error bar would need re-derivation. It would be the least dramatic revolution imaginable. No new object, no explosion, nothing to photograph, just an entire science quietly re-leveling its foundations, and a generation of textbooks rewriting one number in Chapter 1. The resolution, either way, now has a schedule. The Vera Rubin Observatory has begun its decade-long survey of the southern sky, on course to catalogue billions of galaxies with uniform, exquisitely characterized depth, the single greatest cure for the systematics both camps argue over. The square-kilometer array will do the same for the radio sky in the years beyond, multiplying the counts that started this argument 100-fold. The Ellis and Baldwin test, run on those catalogues, will not be a delicate statistical knife fight. It will be an overwhelming verdict, one way or the other, plausibly before this decade ends. Either the excess dipole dissolves under clean data, and cosmology's foundation is certified at a precision it has never enjoyed, or it persists, hardens past any statistical defense, and the textbooks begin the most interesting rewrite in 100 years. Both outcomes are victories. Only one of them is quiet. And hovering behind the argument is a larger pattern that this decade of cosmology cannot ignore. The anomalies are beginning to rhyme. The universe's expansion rate, measured near and far, disagrees with itself at uncomfortable significance. The smoothness of cosmic structure shows related strain. Several independent probes have reported bulk motions and alignments larger than the standard model expects. Any one anomaly is a candidate for eventual mundane resolution. This catalogue has been honest about that all night. But foundations rarely announce their revision through a single dramatic failure. They announce it through a season of small, stubborn discrepancies that keep pointing, from different instruments and different physics, at the same set of assumptions. Whether this is such a season, or merely a coincidence of growing pains in precision measurement, is the live question of the field, and the Count's dipole sits at its center because it interrogates the assumption beneath all the others that we know what standing still means. Physics has, in fact, been in this exact room before, and what happened last time is the reason no one dismisses the question now. At the close of the 19th century, the reigning assumption was that light waves rode a universal medium, the luminiferous ether, and that Earth's motion through it could be measured. The most careful experiment of the age, Michelson and Morley's, looked for that motion and found nothing, an anomaly at the foundations that most experts expected to dissolve into experimental error. It did not dissolve. It sat there, small and stubborn, until a patent clerk took it seriously, and the resolution was not a correction, but a new physics of space and time. The moral is not that today's dipole tension must end the same way. Most anomalies die ordinary deaths, and this catalogue has said so honestly all night. The moral is that questions about absolute motion have a distinguished record of being exactly the loose thread that unravels a century's certainties. When the universe's counts and the universe's light disagree about how we are moving, physics is obliged to tug the thread, carefully, publicly, and for as long as it takes. If the anomaly is real, every available explanation is expensive. Option 1. Our motion is not what the microwave background says. Perhaps the dipole is not purely ours. Perhaps some primordial tilt, imprinted before inflation stretched the cosmos, contributes. That choice severs the universe's rest frame from its light, and precision cosmology inherits an unknown correction. Option 2. The distant universe is genuinely lopsided. The sources themselves are distributed with a preferred direction on the largest observable scales. That choice breaks the cosmological principle outright. Option 3 is subtler exotica. A universe born slightly tilted, structure beyond our horizon leaning on everything inside it. There is no cheap exit. Which is why the counterattack matters, and in fairness, it is vigorous. 2025 reassessments argue the quasar catalogue's masking, scanning patterns and photometric quirks may inflate the significance, and the measured tension drops in some reanalyses. The debate is adversarial, quantitative, and unresolved, precisely the state that precedes either a mundane correction or a change in the textbooks. Upcoming surveys, the Rubin Observatory's billions of galaxies, the SKA radio census, will swell the catalogues 100-fold and settle the count within a decade. I said at the start of the night that we would end on the largest, honest, open question available, and this is it, not because the numbers are the biggest, but because of where the mystery lives. Every other item in this catalogue was out there, a roar in the radio sky, a fog of dying antimatter, threads and bubbles and rings and ghosts. This one is here. It is about the observer. After a century of charting the universe with extraordinary success, the one measurement now in open dispute is the oldest and most personal one there is, how the measurer is moving. Nothing in the universe stands still. We learned that hours ago from a chorus of black holes humming through the fabric of space. The final mystery is that we may not even know, yet, what our own motion is, or whether the universe keeps a still point against which anyone's motion could be finally judged. And there is a fitting calm in that. The stars have kept their appointments all night regardless. Whatever the quasar counts decide, the sun will carry you those same hundreds of kilometers every second while you sleep, exactly as it carried everyone who ever slept before the anomaly had a name. So the catalogue closes, 24 cases, every one still open. That was the promise of this night, and it is worth keeping the promise's meaning close as you drift. Nothing you heard tonight is a failure of science. Each open file stays open because thousands of careful people keep declining to accept an easy answer, and every mystery here is, in truth, an appointment with a balloon's successor, a lake-floated antenna, an atom-counting probe at L1, a laboratory under a mountain, a telescope not yet launched. The universe has answers it has not yet given, scheduled for mornings that have not yet come. That is not a reason for unease. It is a reason to look forward to waking up. And perhaps that is the right final image for a catalogue like this one, the universe as a correspondent with letters still unsent. The roar will be traced or it will not, in balloons yet to fly. The ribbon will obey IMAP's forecasts or defy them. The little red dots will graduate into an answer within years. The diffuse bands may hold their silence another century. The dipole will be confirmed into revolution or audited into a footnote. Every case file you heard tonight has a next appointment already inked in someone's calendar. An observing run, a launch window, a laboratory schedule, and behind each appointment are people who have chosen to spend their one working life on a question they may never see closed. That choice is its own quiet answer to the night's uncertainties. The unknown is not a void. It is a workplace, staffed and funded and patient, and it will still be open in the morning. The night sky above your roof, right now, holds every unsolved thing we have spoken of, the roar, the fog, the harp strings, the bubbles, the tilted count of distant lights, all of it proceeding calmly, as it has for billions of years, requiring nothing from you at all. Let it proceed. Sleep well and good night.